Malik is to join. Sir, you are there. Yeah.
Yeah, yes, I'm always there with you, sir.
Thank you. Thank you.
Yeah.
Shall we wait for a few more minutes?
Yeah, yes, I think the organizers should allow us to start.
Yeah.
Yeah.
Professor S.C. Malik, sir, shall we start the session, sir?
Yes. I'm of course here.
Okay, sir. Good morning to the delegates and participants present here. It is my honor to introduce Professor S.C. Malik Garu, Professor, Department of Statistics, MD University, Rohtak, as the chair of the session. Sir, field of research specialization are reliability theory, sampling and applied statistics. Sir has teaching interests in the field of real analysis, measure theory, optimization techniques, complex analysis, probability theory, statistical methods, reliability theory, and stochastic processes. Sir has published 3 books in the field of real and complex analysis and
Yes,
202 research.
Yes, please. No need to go much. There is a need to introduce Professor K. Srinivas Rao.
Already introduced.
Okay, sir. I request you to occupy the chair and introduce the speaker.
Yeah, please. Thank you.
Yes, sir.
Okay, so now we start the next session, and we start the next session in Hall B. I request all the participants to kindly join this very important lecture. So in this session, we have a very eminent and renowned statistician of India, Professor K. Srinivas Rao. And he is going to speak on a very important topic, that is the new symmetric distribution in regression analysis. And he's a person, although he does not require much introduction because he's a well-known professor of statistics in India and abroad. But it is my prime duty, being a chair of this session, to introduce Professor K. Srinivas Rao with the participants and other dignitaries of the, and as well as to the organizers. I have a few words about him, not taking much time. But Professor K. Srinivas Rao is a professor and working there in Visakhapatnam, Vizag, SV University. And Professor K. Srinivas Rao has experiences of both research and education. He's a good researcher and had published more than 225 research papers so far. And the published publications are in the journals of good repute. Professor K. Srinivas Rao has also supervised more than 50 research scholars. He has guided 54 research students in the fields of mathematics, computer science, and statistics. Really a great contribution on his part so far as research is concerned. And he is a recipient of various awards. He had the opportunity to receive various awards, and one award is Professor Rao got Distinguished Statistician Award by ICSDS, Fellow of AP Academy of Sciences, Fellow of RSI. Dr. Rao has a lot of experience to deliver talks or to conduct conferences of national and international repute. So far, he has conducted 28 international conferences. So, and he is basically a good administrator and a good researcher of the field of statistics. And he has many more things, but due to the paucity of time, it is not possible for me to explain all these things or to say many more things which are not possible to cover within a short duration. So we are very thankful to you, sir, for accepting the invitation of ISPS to deliver this talk on this very important topic. So I request you and welcome you to deliver this talk. Please, I welcome you, sir.
Can I share my?
Yeah, please share.
Host has disabled the participant screen sharing. Host has to allow me.
Yeah.
Host has to allow me. You tell them to allow.
Yeah, I think.
Yeah, it is not accepted.
Okay.
Participant screening. Okay, to save time, before that, Thank you very much, Professor Malik. At the onset, I thank the ISPS organizing committee, especially the president of ISPS, Sir Balakrishna, the secretary of ISPS, Professor S.C. Malik, and Professor Honorary President, Professor Rajshekar Reddy, as well as the organizing committee members, Professor Jayasri, Professor Bhattacharyalu, and others for giving me an opportunity to deliver this Dr. Ravanan's endowment lecture. Dr. Ravanan is a well-known statistician. He worked as the secretary of ISPS and he was propagating statistics in many ways. He has published a large number of publications and he is presently working as the regional joint director of Chennai, Tamil Nadu. And he is propagating statistics by conducting several workshops. I often see his name in the several workshops. He is the recipient of several awards also, and more so, whatever opportunity comes, he used to develop the statistics and to help the young statisticians in several ways. He has guided several people for PhD degrees, and also he is a very good human being. He has instituted a prize. Professor Ravanan's name, the ISPS has instituted the endowment lecture, and I am very happy to deliver this endowment lecture. I thank Professor Ravanan for the support and allowing me to give the lecture on the Ravanan's endowment lecture. Okay, now can I share the PPT? Yeah, it is accepted.
Yeah, good.
It is not coming. Why it is not coming? Are you able to see it?
Yes, yes,
sir.
yes.
Yes, sir. You can
No
go
problem,
ahead.
sir. We continue. Yes, good.
The new symmetric distribution in regression analysis. I was given another 27 minutes time to present this. Quickly, I will try to present the work I have done in this area, the new symmetric distribution in regression analysis. So, we discussed the need for non-Gaussian symmetric distributions, new symmetric distribution, properties of new symmetric distribution, linear models with new symmetric distributed errors, image segmentation and other areas and scope for further research. And some research questions that comes when we do the data analysis. In fact, I am very much fascinated of working with data analysis because I used to go with the consultancy work in many of the industries. When I go for the consultancy, the data that comes in, when we want to do this simple regression analysis, even with multiple regression, the basic assumption of the multiple regression is we make that the error term follows a normal distribution. When the error term follows a normal distribution, we will be coming across the analysis of ANOVA and tests can be performed. But in reality, in some of the data sets, the error term does not follow Gaussian. Then we have a linear model with non-Gaussian errors. And this, how to solve these non-Gaussian errors? How to analyze, how to estimate the regression coefficient, how to do the testing of goodness of fit for the model. And these are some important questions that rise in that. Similarly, in image analysis also, when we do these non-Gaussian images, the analysis will be taken into that. Same thing comes with test-independent speaker identification and skin color identification and several of the other areas where the error term, the residuals may not be normal. They may be non-Gaussian. So in such case, how to proceed further? That is the question. To answer such question, we have one of these things. They are like this. One of the major string in developing the linear models is the assumption about the distribution of the error term. So we all know that under the Gauss Markov setup, the error term follows a normal and they are independent and they are follows normal with zero mean and variance 1. That is the basic assumption we make and we continue. In order to make inferences, it is customary to consider that error term follows the Gaussian distribution. But in some practical situations, the data set may not satisfy the normality assumption due to various reasons, such as they may be skewed or heavy-tailed. So linear models with non-normal errors is very interesting in data science, and now it is a very important thing for finite-dimensional data analysis. So several authors have questioned the validity of the normality assumption. The normality assumption is not always tenable due to various reasons, and alternative distribution should be considered based on the data. Because data, we have to see that what distribution fits for that, and that is to be considered. So the first work in this area is due to Jacques and Thompson in 1970, who attempted to do the work of simple linear regression model when errors are distributed by power distribution. The power distribution is a very important and very useful distribution, and they considered that the error term follows a power distribution. Then Gendler considered in 1976 a linear regression with student T errors. Here, the student T is a very good alternative for this when we see that, because it is also a symmetric distribution, but it is elliptic. And another in 1984, Prosha and Kelsen has critically described the inadequacy of the normal distribution in linear model. They questioned the normality assumption, and they told that many of the cases it may not be the normal. The assumption that we are making may not be very useful. And even if we go by central limit theorem here, the central limit theorem has some regularity condition. The sample size should be very large, and also the distributions under consideration have certain regularity conditions. So these may not be satisfied on that. Hence, we cannot take a shelter under the assumptions of the central limit theorem in such cases. So another model that developed in the regression analysis is the assumption of error term follows a mixture of normal distribution. This is another very interesting part. They are not only just symmetric part, they have taken the mixture of normality, which is not a normal. And recently, Bain et al. 2013 extended the result given by Bain and Tikku, 1907. Tikku et al. Has done a lot of work on that. And again, Isam and Tikku have studied the multiple linear regression models with underlying distribution assumed to be symmetric and student T. They consider only student T. And Lee and Wang, 2013, developed a linear regression model with skew normal errors. So in 2013, with skew normal errors, they consider. And Shafriti and Galberti, 2014, developed a multivariate linear regression model with the assumption that the error term follows a finite mixture of T distributions. A non-normal, but it is a mixture of T distributions. In all these distributions, they consider the error term follows elliptic distribution. They have not tried for platykatic distribution. That is the very interesting part of it. But many data sets we come across in image segmentation, as well as several of the other parts, we come across that the platykatic nature may not serve the purpose. Because of the elliptic may not serve the purpose. They may be more platykatic. We may come across the data sets where it is symmetric but platykatic. So Srinivas Rao et al. In 1977, we have proposed a new distribution known as a family of new symmetric distributions in this to suit these platykatic distributions. And in these platykatic distributions, an alternative to the normal for analyzing various platykatic distributions were given. Because of the time, I am not going in detail about the data set. People can verify. In 1997, we have published a paper in the Journal of Indian Society for Agricultural Statistics journal. There we have published this. You can see the probability density of this new symmetric distribution is nothing but of Fy of y equals to 2 gamma plus y minus mu by sigma whole square whole to the power gamma into e power half of this divided by this. Here the beauty is we can see that this is the product form. That is, a normal distribution is taken and we want to press this. We want to press that so that the kurtosis will be platykatic. So to push that, what is we have is a weighted distribution is to be generated to the normal. It is a weighted normal distribution, more or less we can see. And the weight, how much weight we have to give so that the symmetry should be maintained as well as the platic-cutic nature should come into that. Because if you say that gamma is very large, gamma tending to large, then this become a uniform. So this distribution, the weighted distribution we have developed and we have studied the properties in 1997 as an alternative symmetric distribution where the data is platic-cutic. So for this data, the shapes of these curves will be in this way. The frequency curves, if you see the new symmetric distribution. And if you see that as if you go on the sigma as well as the mu changes, it becomes symmetry comes down. The platic-cutic, the kurtosis comes down from 3. So different values, we can have this kurtosis. So now coming to the linear model, a regression model. We all know that a simple linear regression model is nothing but of this. We say this is here the error. The error term follows a new symmetric distribution. So that is the basic assumption. Still we keep the other assumptions of the Cox-Markov setup and we will maintain the same. Here the error term only we are making as distributed as a new symmetric distribution. Why we require this is when we make a new symmetric distribution, we cannot use the ordinary least squares here. Now it is very important that the maximum, the estimation of the parameters. When we see it is non-normal in linear models, the very interesting and important thing is that we cannot use the ordinary least squares method. OLS does not serve the purpose. We know that because the maximum likelihood estimates of OLS and the other part of this are not same. So we have to look into it. So the maximum likelihood method of estimation we have adopted and to estimate the parameters. So the gamma is to be estimated through directly by taking the moment method first. Once we take the moment method of estimation, we can obtain the gamma parameter. Once the gamma parameter is estimated, then it will be having only 2 parameters, mu and sigma. The mu and sigma, now we can use the maximum likelihood method. Because of the simplicity, we assume that gamma is already identified through the sample kurtosis, and sample kurtosis we can make use and we can take into that, and we can have the required distribution with respect to the sample kurtosis. So the unknown parameters of the new symmetric linear regression model are regression coefficient beta naught and beta 1. So these two can be easily taken. Hello? Already I am in the lecture, madam. We are running the lecture. I am giving my talk. Yeah. Sorry, there is a small interruption from the organizers of the conference. I am worried that my net has gone or something wrong. My voice. I think you are. Is it audible, Professor Malik? Professor Malik?
Sir, you are audible.
Yes, sir.
Yeah.
No problem, sir. We continue.
Yeah. The unknown parameter of the beta, beta coefficients, that beta naught and beta 1 are to be estimated, and the error variance is also to be estimated. So we have taken the maximum likelihood estimate. For estimating that, we know the distribution with gamma 2, that is gamma is replaced by 2. Then we have this distribution with respect to these 2. Then we get a sample of this and we can write the Laplace distribution, the likelihood function. We got the likelihood function of the sample. The likelihood function of the sample is in the usual method. We can write the likelihood function, that is nothing but of this format. Because whenever we are writing that, here it is very important that we are making an assumption that on error term means we are making an assumption on our yi. Since we are making an assumption on our yi can be written as in the linear model that yi minus beta naught minus beta 8. This comes the residual. So the residual in the place of y, we have to replace the residuals in the place of our term. So when we are writing in the place of this, we have all the required likelihood function. We have obtained the likelihood, and log likelihood is also obtained. Once we got the log likelihood function, we got this. Now this is to be optimized. The optimization of this can be done by using the standard optimization, unconstrained optimization methodology. That is the Hessian matrix we considered, and we used the Hessian matrix here. Once we use the Hessian matrix, we can get the normal equations of these three. Three normal equations we will be getting, and we have to solve these three normal equations. Once we solve these normal equations, we will get the parameters of beta naught, beta 1, and sigma square. These we can obtain. Once we get this, we can write these normal equations and solve this. The likelihood estimating I have no explicit solution, because here we can see it is not a unique part of this. Each equation, if you see, this equals to 0, they are not simple. You can see they are not convex or concave. So what exactly we have to see is in the convex function, if they are not a convex, we have to go for optimization. Numerical methods are to be adapted. So we have adapted the Newton-Raphson method to simultaneously solve these nonlinear equations, because these are the nonlinear equations using the moment methods as the initial estimates, moment method estimators under MATLAB. So we have taken the Newton-Raphson algorithm with this parametric set, the theta n, we have taken this, which is the Hessian matrix, and S is the gradient, first in the vector. So the optimization, unconstrained optimization, when we use with Newton-Raphson method, we solve this and we obtain the required value. Once we got that, we have used a sample, because the data, to solve the iteratively, we require data. But here we have taken, to validate the estimates, we have taken a simulation study. With a simulation, what we have is, in the simulation, the sizes of 1,000, 2,000, 3,000, 5,000, and 10,000. These data of sample sizes are taken in the exploratory variable drawn from the new symmetric distribution, generated by using Wolfram Mathematica 9 uniform distribution. Using the generator as the uniform distribution, these samples are generated from a new symmetric distribution with this generalized with these values. And from the generalized new symmetric distribution with beta naught equals to this and beta 1 equals to this and sigma equals to this, the iteration is repeated until the sequence thus obtained converges to the desired degree of accuracy. The results are reported, and especially uses the priority of this computation, and the scale parameters are taken care. So to derive the Hessian matrix, here we used the squares, second order differentiation. Once we have used this, the Hessian matrix is computed. From this Hessian matrix, we have computed the alternatives, and the Hessian matrix is of the form like this. Once we have the Hessian matrix of this form, H is the Hessian matrix, we can have the required consideration that H is the value of this, and we can use the Fisher information matrix. Once we have generated the Hessian matrix, from that we can study the Fisher's information matrix, I beta naught and beta naught square. And once we got that information matrix, this is the information matrix we obtained. You can see the information matrix here. Once you got this information matrix, you can analyze and you can interpret. Likelihood that you can see the simulation results to facilitate the extension of the estimated data with the independent variables of the new symmetric are generated, and we got that. Here we have considered beta naught equals to beta 1 and beta 2 are 4, 2, 3. Mu and sigma are taken as 0 and 1. Obtain the estimates, and we have taken that. Now we have studied under through simulation what are the properties of these estimators. One of the important property we consider is consistency. Because the consistency is the most important consideration, it is clearly that the variance tends to 0 as n tends to infinity in each case. We conclude that the estimators are composed of observations, and it is consistent. The estimators are consistent and asymptotic efficiency, whose variance is small as 10 to Sierra lower bound, then we can say it is asymptotically efficient. So we can easily compute this CRO lower bound for the parameters by using variance of this parametric set H, that is 1 by half minus n into expectation of dou square log fy by dou theta square. That is the information matrix already we have computed. So from that, we have taken the lower bound of the parameters as well as the sigma, beta 1, beta 2 here and sigma here. It is a note that the variance of the estimators in the covariance matrix asymptotically coincide with the Rao-Kramer lower bound, Rao's lower bound. The comparison we have studied whether these ML estimators and ordinary least square estimators are compared in fitting the multivariate linear model with two parameter mu symmetric error, because gamma is already fixed. We call it as a two parameter. Why? Because this gamma is fixed by sample kurtosis in this. So for each estimation technique, bias and mean square errors are computed and presented in the following table. We can see the table here. Here you can see the bias of this is 0.04. Here the bias is 0.01. So bias wise it is more, MLA is more efficient as usual than OLS, and OLS and MLA are not same. That you can see because of the weighted normal here, mu symmetric distribution, and mean square error is also much low compared to OLS estimators. For beta 1 as well as similar thing observed for beta 2, beta 0, beta 1, beta 2, for all these things. So the results reported above says that ML estimators are smaller one step ahead forecast than the other OLS estimators. That is as expected, because when the distribution is assumed, maximum likelihood estimators gives a good estimate than OLS estimators. This we know. And then we have compared with the same data set. If you take the normal assumption, the error is normal, and if the error is a new symmetric, then what will happen? So linear model with normal, linear model with new symmetric distribution. A comparison is made between, suppose the error is taken that no assumption is made, we take the usual consideration, determine the best linear model, the Akai information criteria and Bayesian information criteria, and relative mean square errors are computed. And from this, we choose the best one in this minimum Akai information for which it is there is, you can easily see the difference. Information criteria and model goodness of fit. For a new symmetric distribution, for normal distributed with the same data sets when we have generated from that new symmetric distribution. That is, if the data set actually shows as a new symmetric distribution and it goes as this, the normal does not give the better one. This clearly shows the mean square error for this as well as the other things of the this value is more better and superior. The new symmetric linear model with new symmetric is superior to that once we are taken. This is usual because the data is taken from new symmetric. But here the point is to say that more important consideration is when there is a data, if you don't consider that the distribution, the error term, simply if you do the analysis using your consideration of just the normal assumption, it does not give a good fit to the data. At least some of the data we have here and we have seen the comparisons are made, and also we have taken a generalized symmetric distribution this, and we have also continued the application. We have taken a data set of 202 athletes on sports running on that, and their BMI and RCC and WCC and PFC. This data is taken from that Australian players published in the journal, and from that data we have tested that, and the error term is deviated from the normality. The test results clearly shows that they are non-normal, and the skewness and kurtosis, if you see, they are deviate from that. Therefore, we have taken this model and we have fitted that. And once we have fitted it for the data set, the linear model with that, what we have taken is a more better than the linear model already we have considered. That is, we can see the estimates. The estimates that were taken here are different from the estimates that were taken here, and the standard errors also there, and the Akai information, if you see, that is also more. The more is there, that is value we will be getting. And then another interesting results we can see is usually the error terms or anything we take, they does not have an infinite range. They will have only a finite range. So the generalized new symmetric distribution, what we have given a family of distribution, that was truncated on both the ends. Once we have truncated on both the ends, there we have got the truncated distribution on that, and the truncation is taken over and above, and we have a truncated distribution, the truncated new symmetric distributed errors. So we have also considered the model, linear model, regression model with truncated new symmetric distributed errors, and we got the estimation of the model parameters. Here we have taken the same model and we have fitted that, and with a sample size of 10,000, we have run the simulation study also, and we obtained the likelihood estimates, and a simulation study is conducted with respect to the truncated generalized new symmetric distribution errors, and we got that this is gives more better than the earlier part of the thing, what we have considered in that. Here in that, we consider from that the data. When we have taken the sample size from 100,000, that as we see the variance of this, when the sample size increases, automatically the model gives a very good fit to the given data, and also it gives the confidence limits were also taken and destabilized. When n increases, the confidence intervals are simulated, and the simulation we have taken into that, and we have considered this. And the bias and the parameters with respect to the generalized truncated generalized new symmetric distribution. That is also we have taken, and the bias we have computed, and mean square errors we have computed for the likelihood estimates as well as the OLS estimates. And these we consider that compared with this, we have done the linear model with normal as well as DTN. Again, the truncated model gives a very good fit compared to the earlier model what we have in hand. And we have taken that model with small values of criteria potential in doing that, and we have applied this to another data set also that was available from that with the same part of the thing. And we have seen the test for departure of the normality, and at the data is departed from this, and estimation of the model parameters, and we have computed all that, and it is shown that the proposed model or that gives a better fit than the earlier linear model. So here it is very important that we have to consider the normality assumption in the linear models when we are doing it. Here a lot of scope is there now. Now this all analysis we have done by simulation study. But empirically, if we want to do the testing of hypothesis, still we are lagging behind in developing a analysis of variance test for goodness of fit, like a F-test. F-test under normal errors like a new symmetric and other. And that part of the thing is be very useful. And similarly, testing beta naught and beta 1, not with the t-test, because the t-test is no more useful here. The basic assumption of normality is deviated. So a lot of work can be done with the linear regression with normal errors. In fact, the theoretical work is more to be done, and then data analysis can be carried out. Because all the packages, if you see as a SAS, SPSS, and Minitab, and these packages, they are giving with the respect to the normal error. But non-normality is that. And people say when there is a non-normality, we can use the transformation. But transformations may not serve the purpose always. And it is the difficulty in that. And so one should be very careful when we are taking this non-normality in the error. That is very important and very interesting part of thing. Because in the nowadays, the computational facilities are there, and more technological evaluations has came, people can work on developing the more non-normal distributions. In fact, we have also tried for generalized Gaussian distribution with a non-normal error, but still we are going with the simulation studies. But empirically, we can derive a distribution like F. It will be very useful here. And with this, I thank the organizers for the given opportunity. Thank you. Thank you. I hope I am in time.
Yes, sir, definitely. Really, I appreciate that your time management is very perfect. And you finished the talk within the given time. Really, I appreciate first. And one more thing is that if any question on the part of the audience please, they are free to raise any question. Professor Srinivas Rao is available with us. Yeah.
Sir, as you said that the assumption of t test is violated here.
Yeah, exactly.
Sir, is it also happened in Z test and other test?
Yeah, exactly. When you go for linear models, we use two tests, usually for testing the regression coefficients as well as the goodness of test of the model validity. So one is t-test or z-test we use for beta coefficients. So the basic assumption is the error term follows a normal. That assumption is violated. Since that assumption is violated, we cannot use the t-test directly. And similarly, the another assumption of getting the f-test. F-test is also here, we cannot use the goodness of fit. Both will be violated. And
Yeah.
we have to develop our own for that.
Yes, yes.
Okay. Sir.
So, Professor, can we consider this distribution as a particular case of normal distribution or otherwise?
It will be it includes normal also. It is not a particular case. But normal is a mesochatic. This is a family of platychatic. So
Yeah.
the gamma tends to 0. Gamma becomes 0. All weight that was given become 1. When it becomes 1, it is a normal. So
Okay. So is there, what you say about the leptocultic nature?
Yeah, leptochatic nature, we are trying with generalized Gaussian, which includes both the leptochatic and platychatic distribution.
Oh, good. So really wonderful. Any other question on the part of the audience? Yes. So let me thank the speaker, and really a very interesting lecture and informative lecture in the area of distribution. And really you developed a very good distribution, which can be an alternate to the normal distribution so far as platychatic nature is concerned. So thank you very much, sir, Professor K. Srinivas Rao. Let me thank once again Professor K. Srinivas Rao. Thank you very much for nice lecture. Thank you, sir. I hand over the session to the organizers.
Thank you, Professor S.C. Malik Garu, for chairing the session. Now it is my honor to introduce Professor K. Muralidharan Garu, ex-head Department of Statistics, Faculty of Science. Professor was ex-head of Department of Statistics, Faculty of Science, the Maharaja Sayaji Rao University of Baroda, Vadodara. Sir was also the Director of Population Research Center, MSU Baroda, during 2011 to 2016. Sir's research interests are in the field of statistical inference, applied stochastic point process model, reliability and life testing, industrial statistics, artificial intelligence, and machine learning, and quality and Six Sigma. Sir is an internationally qualified Six Sigma Master, Black Belt, and quality trainer from Indian Statistical Institute, Bangalore. Sir contributed around 140 publications in reputed national and international journals. Professor is also the coordinating editor of Journal of Probability and Statistical Science, published from Taiwan, associate editor of many journals, including Journal of Indian Society for Probability and Statistics, and many more. Sir had won a number of awards and fellowships, including the Distinguished Statistician of India Award from Indian Society for Probability and Statistics, India, and Commonwealth Academic Fellowship sponsored by British Council, UK. Sir was awarded the Best Science Teacher Award in Mathematical Science by Gujarat Science Academy, Ahmedabad in 2017. Professor was also awarded the Young Emerging Future Leader of Quality and Reliability by Society for Reliability Engineering, Quality and Operations Management, Sweden in 2015. Sir is a principal member of the Bureau of Indian Standards, New Delhi since 2008. He has been the Secretary of Indian Society for Probability and Statistics for the terms 2013 to 14 and 2015 to 16, and Vice President from 2019 to 2020. Now I request you to occupy the chair and introduce the speaker.
Thank you very much, madam. Good morning to all of you. Can you hear me?
Good morning, sir. Good morning.
Yeah, I'm audible, right?
Yes, sir. Yes, sir.
Yeah, you are audible.
Okay, fine. Thank you very much. Nice to see you, Professor Parameshwar.
Yeah, thank you, sir.
We have been meeting many
Yeah.
of one, right?
Yeah, thank you.
I chaired your sessions also earlier also. So
Yes,
I'm so
yes,
happy
yes,
again.
yes.
Okay, thank you, the lady who introduced me. I'm sorry I could not name that lady. Thank you very
Thank you,
much
sir.
for the organizers for giving me a chance to chair this session. Okay, so this is reliability engineering session number 1. And the speaker is Professor Parameshwar V. Pandit. He is from Bangalore University. A very nice researcher, nice presenter, a very nice individual, and a human being. So we have been meeting quite often at various places in scientific forums, conferences, etc., etc. And so I'm happy again to chair the session where the speaker is Professor Parameshwar V. Pandit. He's going to talk on statistical inference for stress strength reliability of S out of K system based on upper records under new viable Pareto distribution. I'm sure this is going to be really a good, wonderful talk. Okay, so Professor, I would request you to have your presentation for about, I think it is total 30 minutes.
Yeah, 20 minutes.
Around, okay, 25 minutes. Okay,
Yeah,
we'll have
20.
some discussion at the end of it. Okay,
Yeah.
so
yeah.
nice. I
So
leave it to you, sir. I leave it to you. You can start.
Okay.
Start your talk.
I take this opportunity to thank Professor Muralidharan. Of
Thank
course,
you
we
very
have,
much.
as he already mentioned, we have met in several occasions, and he has shared my sessions also, my talk. And I also thank the organizers for giving me this opportunity, particularly Professor Jayashree Bhattacharyalu, and also the ISPS President, Professor Balakrishnan, Rajshekhar Reddy, and Professor Malik and others. And I want to share my screen. Okay, it's allowed.
You can share, sir.
Yeah.
Yes.
Just
Yes.
a minute. I think
It's coming up. Okay.
coming,
Okay.
but it's not in the first page. Yeah.
Slides. Okay. You can change the.
I have to make the.
Take your time. Take your time.
Okay.
Very good. Yeah. What happened?
Just a minute. I'll just do that.
Okay. Okay.
Is it visible?
Yeah, it is visible. It is visible.
Visible, right? But it's.
Make sure that it is in slideshow mode. Make sure that it is in slideshow mode.
Okay.
Okay. You please enlarge it.
Now I think it's fine. Is it okay now?
Sir, upstairs page view is there. Click on that, sir. Page view.
What is that?
Page view. In upper tab, page view is there, sir.
I'm not unable.
No, left side, sir. Left side is there. Cursor, move your cursor, sir.
Okay.
Here, sir, page view. After headings are there, no, sir. Page view is there. Sir, see the headings, sir. Page view, reload, add text, all are there, sir.
No problem. Take your time.
Now you can see it right now. Shall I start? Hello.
I don't know. I could not see the screen.
That's why I'm unable to.
After that, you click that.
Madam, are you able to see?
Yes, sir. Yes, sir.
From the organizer's side.
Yes, sir. Yes, sir.
Now it's visible, right?
I can see the presentation, sir.
Okay.
Okay, please start then. Please start.
Okay.
Please start.
So again, I thank all the organizers for this opportunity. The title of my talk is, as already mentioned by Mr. Muralidharan, Statistical Inference for Reliability of Multi-Component Strength Model for Variable Pareto Distribution, new Variable Pareto Distribution based on records. I think there is a disturbance.
Yeah, I request all other delegates to mute their microphone, please. Okay, sir.
So
Okay,
my
thank you.
plan of presentation is as below. So I just state the problem with an introduction. That this introduction includes review of literature, and I just bring in what we mean by stress strength reliability for S out of K system, and then of course we obtain maximum likelihood estimator of reliability, and I am bringing in a likelihood ratio test for a particular. I will explain it afterwards, and then I am going to obtain the base estimator, approximate base estimator for the reliability of S out of K system. No, of course, it's very difficult to get a closed expression for base estimator reliability. We are getting an approximate base estimator using an approximation technique given by Lindley, and followed by simulation study. In simulation study, we will be considering empirical mean squared errors and to compare the different estimators obtained here. And of course, I just give a one real data analysis, and I'm concluding with some remarks and conclusions. Okay, the estimation of multi-component system reliability, particularly S out of K system, is considered where the system has K independent and similar or identical components under stress strength setup. The system reliability is evaluated assuming new variable Pareto distribution that will be explained, that will be given after in the next slide, distribution of our stress and strength variables. And here we should make note of it that the stress and strength variables are independent but not identically distributed. So when we are developing a likelihood ratio test for testing equality of scale parameters on which the reliability of the system depends. In this setup, the maximum likelihood estimator or the Bayesian estimators of system reliability is obtained based on upper records, and approximate base estimators are also obtained using Lindley's approximation technique. Here I am not going to present the maximum likelihood estimator under the SRS scheme. However, it is available in the literature, and I'm comparing the mean square errors of base estimators with maximum likelihood estimators. And of course, the estimation procedures are illustrated using a real data set. What is stress strength reliability in this setup? The term stress strength reliability typically refers to the evaluation of probability of y less than x, where x is the strength and y is the stress. Such a system fails if the stress exceeds the strength. This is single component stress strength reliability. Birnbaum and McCarthy in 1958 developed stress strength reliability, which was introduced by Birnbaum in 1956. Several papers have been published by considering different choices of stress strength distributions. I'm not going to list all. A few of them I'm going to do that. See, what is S out of K system? The S out of K system liability in a stress strength setup was first introduced by Bhattacharya and Johnson in 1974. The S out of K system reliability can be described as below. The system having K components with their strength as x1, x2, x1, xk being independently identically distributed random variables, and each component is experiencing a random stress y. A system is said to be S out of K system in a stress strength environment if the system works if at least S component strength exceed the stress. The application of S out of K system can be seen in many real-life situations, particularly in industry and military. For example, in an electrical power station containing 8 generating units, which produce the electricity only if at least 6 units are working. The demand for the electricity of a district is fulfilled only if S out of K windrows are operating all times. That is, at least 6 out of the whole windrows are operating all the times. This is taken from Q and So 2003. The estimation of multi-component stress strength reliability for S out of K have been extensively investigated by many authors in the literature. The multi-component stress strength reliability estimation is considered for log logistic, generalized exponential, inverted exponential, Rayleigh, Burr type 12, and inverse Rayleigh distributions, respectively by Rao and Kantam 2010, Rao. There are 3 papers, 2012, 13, 14, and Rao et al. 2015. Kijislasan and Nadar, 2015 and 16, consider the estimation of multi-component strength reliability using both classical and Bayesian approach when the underlying distributions are Weibull and bivariate Kumaraswamy. This paper considers stress strength reliability of S out of K system when the underlying distribution is new Weibull Pareto distribution. So the new Weibull Pareto distribution was introduced by Tahir et al. In 2014 and discussed by Nasiru and Legutera in 2015. So the distribution has the following density function fx given here. It has 2 parameters, beta and delta. And we have the distribution function as capital Fx here. So we also have the hazard function, which is given by this hx. This is beta delta by theta into x by theta to the power beta minus 1, and delta and beta, delta, beta, theta, 3 parameters. These are the 3 parameters. Here you can see that if beta equal to 1, the failure rate is constant. And of course, as we know, this makes NWP distribution suitable for modeling systems or components with constant failure rate. So if beta is greater than 1, the hazard function of x, which makes NWP distribution suitable for modeling components that varies faster with time. And if beta less than 1, the hazard function of x makes NWP distribution suitable for modeling components that varies slower with time. Okay, next we are considering the estimation of system reliability using upper records. So the main idea of record values was introduced by Chandler in 1952. These record values have become important field of research in recent years due to vast applications in force, hydrology, and life tests. The advantage of using record values is the reduction in number of measurements to be made as compared to that in complete sample, and the measurement saving can be done when the measurements of the experiments are expensive in case of destructive experiments. The definition of upper record values as in the literature is as below. So for a sequence of independent identically distributed random variables, x1, x2, so on, a random variable xj is said to be an upper record if xj is greater than xi for every I less than j. An analogous definition can be given for lower records. Use of record values in estimating system reliability in a stress strength setup has been studied in literature by many authors for various distributions. To mention a few, Shi Wang 2013, Tervirti Z and Ahmedov 2016, when the underlying distributions are exponential and 2-parameter bathtub shaped. So now the system reliability. So the reliability of reliability of stress strength and the stress strength setup is the of a sort of system is the following. As I told in the beginning, Bhattacharya and Johnson 1974 developed the reliability of a sort of K system in a stress strength setup as below. Let the random variables y, x1, x2, so on, xk be independent, and gy be the cumulative distribution function of y, and the fx be the common cumulative distribution function of x1, x2, so on, xk. So the reliability in a multi-component stress strength model, that is S out of K system, developed by Bhattacharya and Johnson, is the following. This is RSK. It is given in 1. The system with K identical components functions if S or more components simultaneously operate. Now, the system is subject to a stress Y, which is a random variable with distribution function G. The strength of the components, that is the minimum stresses to cause the failure, are independently and identically distributed variables with distribution function F dot F. Then the reliability of the system is given in equation 1. In this setup, the reliability of the system is this. Now, we use this to derive the reliability of S out of K system when the underlying distributions, stress variables have new variable parameter with delta 1 theta beta and Y follow delta theta beta. So here we can see that we only delta 1 and delta 2 are different. So the x1, x2, xk and y are identically distributed if delta 1 equal to delta 2. And only they differ with reference to delta. So this is the case which we have considered. Then the reliability of the system, S out of K system, is given by this expression. So, and here we can see that, say, if delta 1 equal to delta 2, this becomes, this reliability doesn't depend on any of the parameters. That is, it doesn't depend either on delta, theta, or beta. So, hence, estimation, it can be noted that the case when stress and strength are identically distributed according to new variable Pareto distribution with parameters delta, theta, beta, the reliability of S out of K system does not depend on the parameters. Hence, the estimation of reliability of the system suffices to estimating RSK only when the stress and strength variables are not identically distributed. That is, delta 1 not equal to delta 2. So, for that, to check whether delta 1 is equal to delta 2 or not, we conduct likelihood ratio test. So for that, first we consider deriving maximum likelihood estimators of the parameters. Okay. And again, it is my setup is only based on record value. So now I have a upper records U1, U2, UT1, and for X. And for Y, we have V1, V2, so VT2 with the upper records for this. Then the likelihood functions are given by, say, L delta 1 theta beta is this, and L delta is in general. L delta 2 theta beta is this. So now, for our purpose, if we replace F and capital F by our distribution, that is new Pareto distribution, we get the likelihood function for X as this and Y as this. And now, if you multiply this, we get the likelihood function for the given setup. So, take the log likelihood. The log likelihood is this, and then we obtain the likelihood equations. See, dou log L upon dou delta 1, dou log L upon dou delta 2, dou log L upon dou delta theta, and this L is general. There's a small error that I have to make it L1 and L2. So L is L1 into L2. Okay, so and this is these are the likelihood equations to estimate parameters delta 1, delta 2, theta, and beta. So now we can see that the likelihood equations are very complicated, and it is very difficult to obtain, not very difficult, it is impossible to obtain a closed form expression for that. However, the maximum likelihood estimator of delta 1, delta 2 are obtained in terms of beta and theta, and the beta and theta are unknown. So we have to find out the estimate for beta and theta. So that is obtained, that can be obtained by solving the nonlinear equation of the form this H beta equal to beta, where H beta is this. It is a nonlinear equation, and also H theta equal to theta. So by iterative techniques, beta hat and theta hat has obtained, and we substitute the ML estimates obtained for beta and theta, and we get the delta 1 hat and delta 2 hat. And after substituting delta 1 and delta 2 in the expression RSK, we get RSK hat that is MLE for RSK hat. And of course, we can see that MLE, if we want to use construct the likelihood ratio statistic, we need to obtain the MLE under H0 also, that is delta 1 equal to delta 2 also. There also we have obtained delta hat, beta hat, and theta hat, and it's not there in the slide. Anyway, we have already obtained that. That is missing here. I'm sorry for that. Okay, then likelihood ratio test for equality of scale parameters now, because if delta 1 equal to delta 2, there is no there is no necessity of estimating RSK, because it doesn't depend on any of the parameters. Okay, so again we have two samples, U tilde and V tilde. These are the records, and we obtain the likelihood ratio L mu is equal to L1 into L2, and we have to construct likelihood ratio test for testing H0 delta 1 equal to delta 2 equal to delta against H1 delta 1 not equal to delta 2. So now for that usual procedure, we have obtained lambda mn as the likelihood ratio statistic, and mu naught hat is delta hat, theta hat, beta hat, and for mu hat it is delta 1 hat, delta 2 hat, theta hat, beta hat. Hat is missing. Then you have LMN lambda nm as L of mu naught hat xy by this. So the test criterion is to reject H0 if lambda nm is greater than C. So to obtain this C, we need the null distribution of lambda n. So null distribution finding null distribution of lambda nm for small samples is very difficult. Of course, empirical null distribution can be obtained, so that is under progress. However, the asymptotic distribution of this -2 log lambda mean is chi-square with 1 degree of freedom. Hence, the test criterion is to reject for large values of -2 log lambda n. So now this so the behavior of likelihood ratio test obtained here in terms of empirical power is evaluated for n equal to m equal to 25 to 30, 40, 50, etc. For different combinations of delta 1, delta 2, theta, beta are considered for evaluating empirical powers. And I'm not giving you the tables here. Anyway, however, the following are the observations from the tables. The power of LRT increases as the difference in parameters, delta 1 minus delta 2 values increases. The power of the test increases as the sample size increases. Both the above observations reveal that the likelihood ratio test constructed here possesses the desirable property of a reasonable test, as the chance of rejection is more when the value of the parameter moves away from the parameters under the null, and test is consistent, of course. So now we are estimating RSK using Bayes estimator. Maximum likelihood estimation already have been done. So based on the decision of likelihood ratio test, the estimators of RSK are obtained. And then maximum likelihood estimators of RSK are obtained. And if the likelihood ratio test rejects H0, then using invariance property, MLE of RSK is given by this. So next, the Bayes estimator of RSK is obtained for S out of K system under stress strength reliability, assuming prior distribution for delta 1, delta 2, theta, and beta as below. Here we assume that all the parameters delta 1, delta 2, theta, beta are random variables and have independent gamma priors with parameters Ci, delta hyperparameters. The PDF of gamma distribution for the random variable X is given by this, and the joint prior is the following. The corresponding joint posterior distribution is given by phi of delta 1, delta 2, theta, beta, given the sample XY is this, and now you can see that this joint posterior distribution itself is very complicated, and evaluating that is not possible in many, here at least. So we know that the Bayes estimator of R under square norm loss function is the posterior expectation. That is given here. RSK hat B is integral RSK into phi of this, and the evaluation of the posterior mean is not tractable. However, approximate posterior mean can be obtained using Lindley's approximation method. And the Lindley's approximation method is the following. So this procedure is employed to get posterior expectation of the function u lambda. If you have this expectation of u lambda as in this way, then you can evaluate expectation of u lambda in the following way. And I'm skipping all these mathematical details, and we get base estimator using all these quantities. And in Lindley's approximation, these quantities, ui's, uij's, lijk's are all derivatives, and which are the functions of parameters. Lambda, here lambda is taken, lambda, then we are replacing that by its maximum likelihood estimator. And so that it will not be a function of unknown things. So then we get a base estimator. So next is
Can I request you to conclude in 5 minutes, sir?
Yeah, 2 minutes.
Okay,
no problem. So a simulation study is conducted to compare the different estimators, that particularly maximum likelihood estimator and base estimator. And this comparison is done through mean squared error criteria based on 1 lakh random samples of sizes n and m. We have evaluated empirical mean square errors for different sets of values of delta 1, delta 2, theta, beta for S out of K system. However, we present the results only for this combination of parameters. And of course, we have the results for different possible sets also. However, the observation is similar, and for the sake of illustration, we are giving only this. Okay, the following is the table. Here you can see that we have taken delta 1 equal to 0.5, delta equal to 0.1, theta equal to 1, and beta equal to 1, and prior 1. Prior 1 is the given here. The prior 1 is this. That is C1 equal to 2, C2 equal to 7, C3 equal to 4, D1 equal to 3, D2 equal to 5, D3 equal to 2. This is prior 1. And we can see that we have estimated using MLE as well as maximum likelihood method as well as Bayes method. And here you can see that the mean squared error is 0.0091 for MLE under SRS. Of course, this is 0.000077. It's both under, not under SRS, it is under record values. And of course, consistently, uniformly, you can see that base estimators are better. Many places, MLE and base estimators very close in all the considered set of values for deltas. A real data analysis also is presented using the data given by Zai et al. And we have evaluated MLEs for all the parameters. We have obtained MLEs for all the parameters using this data set. And we have seen that the data set, viewable Pareto distribution is a good fit for this. And we have evaluated obtained the estimates. And summary, the multi-component system reliability, which has K component, independent and identical stress components, and each component is exposed to a common stress by assuming stress and strength variables follow viewable Pareto. The system reliability is estimated using MLE maximum and Bayesian approaches based on record value or not with reference to scale parameters. And the simulation study results indicates that MSEs of the system reliability decreases as the sample size increases. Bayes estimator performs better than maximum likelihood estimator The estimate is derived here I illustrated using real data. So, and there are some of the references. Okay, thank you. I take this opportunity to thank again the organizers for giving me this
Thank you very much, Professor Pandit. Excellent work.
Thank you.
Excellent work, excellent presentation.
Thank you, sir. Thank you.
I leave it to the audience for any questions, please.
Yes,
Let's
sir.
wait for a couple of minutes. Yeah.
Sir, I would like to request you to share justification for your priors proposed, sir.
Priors are conjugate priors.
Conjugate
Priors are conjugate priors.
for all the parameters, sir.
Yeah, for all the parameters, it is priors are conjugate priors.
Okay, thank you, sir.
Any questions, please? Any other questions? Okay, Professor Pandit, it was really a nice presentation, and work is related to very close to order strategies once you consider the record values, right?
Yeah, but sir, I'm unable to hear you. There is a
Okay,
disturbance.
so this is based on order strategies, right?
It's record values.
It is record values. Once you consider
Yeah, records,
actually,
upper records.
Yes, there will be some kind of natural ordering, right?
Yeah, natural ordering. Yeah, that will be.
So,
Yeah, I
yes.
can say that it's a generalized order statistics kind of a thing. Yeah.
all right, generalized strategies. Okay. Okay, so testing is done. You have what else are you, base estimation is also proposed. What
Yeah.
else are you going to propose now? What is your extension work?
Yeah, as an extension, see, I have started with only one parameter common. I think we can keep one of the only one of the parameters as it is identical only if two parameters are different. So we are considering the work when two parameters are different.
Okay.
Yeah, because I mean the mathematics is very complicated if we make it all the parameters are different. So we are trying in that direction. Let us see. One of my students is in that
publication related.
Yeah, this is already published in a book by Modern Applied Statistics, published by Springer Nature.
Okay, very nice. Just for your information, we also have a publication recently based on record values for Rayleigh distribution. Rayleigh distribution, yes.
Okay. Thank you, sir. Thank you. Can you please send me that reference?
Oh, yes. This is also published.
I'm so grateful to you if you can send that reference.
Oh, yes. Today itself I will send you.
Okay, sir.
Okay, so with that comments, we'll stop the presentation and stop the session. So let me also thank Professor Jayashree, Madam. So you introduced me. So thank you so much, Professor Jayashree, your colleagues, and the Department of Statistics, Usmania University, for giving me an opportunity. Thank you once again, and over to you, Madam.
Thank you, Professor K. Muralidharan Garu, for chairing the session. I am Lakshmi Himaja on behalf of the department.
Okay.
Sorry, sir, you're not audible.
Oh, I see. There is some connectivity issues here.
Yes, sir.
Okay, thank you very much. Continue.
Thank you, sir. Now, I would take the opportunity to introduce Sudhish Kumar Kattumanil Garu to introduce the contributory paper session for the time slot 12 to 1:35. Sudhish Kumar Kattumanil Garu is an associate professor, Indian Statistical Institute, Chennai, India. Sir has published 45 research papers and 2 books. Sir's research interests are in mathematical statistics, reliability and survival analysis, and equality measures. Sir's fellowships and recognitions are Mathematical Research Impact Centric Support 2018, International Travel Support 2017, DST Government of India, Indo-US Research Fellowship 2013, NBHM Postdoctoral Fellowship 2008, UGC CSIR Junior Research Fellowship 2003. And sir, the awards received by sir are Jan Tinbergen Award for the Young Statistician from Developing Countries 2009, International Statistical Association Netherlands, and US Nair Memorial Young Statistician Award 2006, Indian Society for Probability and Statistics. Now, I request you to occupy the chair and conduct the contributed paper session in the stipulated time, sir.
Okay, thank you for the nice words. Anyway, we have this section dedicated to reliability engineering. This up to 1:35, and we have around 10 speakers. So one can go 40, serial number 34 to 43. So can I, everybody is presented, or because accordingly we can have the time schedule. No. Yeah, you can present then about 1 minute per 10 minutes. You have to finish everything in 10 minutes. Okay. So first I will call SK Chauhan. Was there SK Chauhan?
Yes, sir. I am present.
Yeah, you can. Please complete within 10 minutes. Okay. That itself little higher, but you're trying to finish.
Okay. Good morning, all of you. I am audible. Am I audible?
Yes, sir.
Yes.
You are audible,
You
sir.
can make it a full view screen.
Good afternoon, all of you. I am Dr. S.K. Chauhan, Assistant Professor, Department of Statistics, Sahit Rajguru College of Applied Sciences, Women's University of Training. My research title is Reliability Analysis of a Non-Series Parallel System with Different Flow of Information. Outline of the research work. First one is introduction, notations, system descriptions, particular cases, reliability measures, for arbitrary values of the parameters, discussion and conclusion, and lastly references. Over the years, the manufacturers have been stressing on the determination of best possible design of the components in order to improve reliability of their product. The existing literature on reliability indicates that system performance can be improved by using either components of good quality or by adopting proper repair policy. The structural design of the component has also been given a considerable importance in order to improve the reliability of the system. Balagurum Swamy in 1984 provided that a parallel structure of the components is better than that of the series structures. The reliability of a systems having constant failure rates of the components with series parallel and parallel series structures have been carried out by the Chauhan and Malik in 2016. Again, 2016 and 17, Chauhan and Malik also analyzed reliability of series parallel and parallel series systems with bevel failure class. The study reveals that system having series parallel structures of the components is better than that of parallel series structures. In practice, system is not always simple series or parallel structures. A complex system on simplification can produce a non-series parallel structure. Several methods have been adopted to use the evaluation of non-series parallel structures. In 2015, Ijati and Rasoli evaluated system reliability using linear exponential distribution functions. The work of this paper indicates that fold duplication method is better than that of the var duplication method. It is not possible to make a general statement for comparison between reduction and duplication methods. The logic diagram techniques can also be used to handle such type of a non-series parallel structures. Each path contains elements whose successful operation can lead to the success of the system. The system works successfully if there is at least one continuous path between in and out terminals. The present study is devoted to the reliability and mean time to system failure analysis of a non-series parallel systems of 5 components. The expressions of these reliability measures are derived by considering bevel failure large of the components. The reliability and MTSF of systems are obtained for arbitrary values of the parameters and for some special cases of bevel distribution, that is Rayleigh and exponential distributions. The effect of failure rate of the component, operating time of the components, and shape parameters is examined numerically as well as graphically for arbitrary values of the parameters. The logic diagram techniques is used to determine the reliability features of the systems. Notations. These are some common notations which are used in this paper. RST be the reliability of the system, RJT be the reliability, path reliability of the system. Because in this systems, considering only 3 paths, PIT be the reliability of the ith components, CI be the components, PT indicates the reliability of identical components, lambda be the scale parameters. But in this paper, we consider the failure rate of the components. T be the operating time of the components, beta be the shape parameters, and T be the lifetime of the system. System description. This is a non-series parallel system because this system not contains only simple series or simple parallel structures. In this figure, there are 5 components. Considering the 5 components, the arrow indicates the flow of information. Such systems can be analyzed by logic diagram techniques as well as by the cold and word duplication methods. In logic diagram approach, we convert the given system diagram into a logic diagram techniques between a simple series or parallel path between the in and out terminals. Each path contains components whose successful operation can lead to success of the system. For the successful operation of the systems, there should be at least one continuous path between in and out terminals as shown in the figure 2. In this figure, the figure second indicates a simple parallel series structure. Here it is important to note that the paths are not independent because some subsystems find place in more than one path. The reliability of these systems can be evaluated by the method of parallel series configurations. Let us suppose that the component CIT, which is already discussed in the previous slide, in the path first reliability becomes R1T because path first contains only 2 components C1 and C2. Then the path first reliability becomes P1T. Similarly, part 2 reliability be the P1T into P2T and P4T because path second contains only 3 components and similarly path 3 contains only 2 components and the path 3 reliability, third reliability becomes this. Therefore, the system reliability in this case, the system perform the parallel series system, then the formulas of parallel series system, the system reliability becomes this. For identical components, the system reliability becomes as shown in figure equation 2. Reliability measures. In these systems, we consider a bevel failure large for the reliability of the components. PIT be the reliability of the ith components according to the bevel failure large. Then from equation 2, the system reliability becomes this and so in figure 3. And MTSF be the integration of reliability with respect to the time, then the MTSF becomes this and so in equation 4. For identical components, the system reliability so in equation 5 and MTSF in equation 6. Numerical and graphical representation by the bevel failure large. In this table, we fix the operating time of the components and increase failure rates as well as shape parameters of the component. Then we can say that the reliability go on decreasing and increasing the shape parameters and failure rates of the components. And this is the graphical representation. MTSF also follow the same trend like reliability. In this table, MTSF also go on decreasing when increasing the failure rates as well as shape parameters of the component. Again, table third. In this table, we fix the shape parameters of the component. But in table first, we fix the operating time of the component. And in this table, we can say that the reliability also go on decreasing when increasing the failure rate of the components as well as operating time of the components. And next table, in this table, we fix the operating time of the components and increasing the shape parameters as well as failure rate of the components. In this table, also reliability go on decreasing. MTSF follow the same trend like reliability. And next table, we increase the operating time of the components.
Please conclude in 1 minute. Okay.
Okay. Reliability measures by Rayleigh distribution, because we know that the Rayleigh distribution is a special case of variable distribution when the shape parameters beta considering 1. Then the component reliability becomes beta. From the equations first, the system reliability as shown in equation second and MTSF shown in equation 8. For identical components, system reliability shown in equation 9 and MTSF in equation 10. Again, in this table, we increase the operating time of the components as well as failure rate of the components, and we can say that the reliability go on decreasing and increasing the operating time of the components as well as failure rates of the components. And MTSF will also follow the same trend. This is the graphical representation. Again, this is the graphical and numerical representation. The reliability measures by exponential distribution. We know that the variable distribution follows exponential distribution, and the shape parameters is equal to 0. Then the system reliability becomes RST and shown in equation 11 and MTSF. Again, this is the numerical representation by the help of exponential distribution, and in this table we increase the operating time as well as failure rate of the components. Again, we can say that the reliability go on decreasing when increasing the failure rates of the components as well as operating time of the components.
Please conclude. Please conclude.
Finally, we can say that in non-series parallel structures, the exponential failure large is more beneficial as compared to parallel failure large and relative large. These are some references. Thank you.
Ashley is there? Ashley is there?
Yes, sir.
Yeah. Please present in 10 minutes itself, and you can skip the introduction part. Okay, some of the introduction part, so that okay, start it. Anyway,
Okay,
you can start. Thank you. See, sorry, actually, thank you, Chauhan, for your presentation. I was in a hurry to call the other person. Okay, actually, you can start.
Is my screen visible?
Yes, carry on.
Okay, sir. Good afternoon, all. I'm Ashley Elizabeth Koshi. I'm a research scholar, University of Kerala. The title of my talk is Estimation of Multi-Component Stress Strength Reliability for Exponentiated Gumbel Distribution. This is a joint work with my guide, Dr. Manoj Chako. These are the contents of today. Okay. Stress and strength, but we may or may not be familiar with stress strength reliability. So let us go through the some terms which we are going to use throughout this presentation. Okay, stress strength reliability. It is defined as the evaluation of reliability of components in terms of two random variables, stress and strength. If the stress exceeds the strength, the system fails. In other words, we can say that our system will survive only when the inbuilt strength exceeds the experiencing stress. So mathematically, we can express system reliability R as probability of X greater than Y. Here X is the strength and Y is the stress. But here we are considering multi-component system. A multi-component system means our system contains more than it. Here in particular, our system contains total K components and our system will survive only when at least S of the K components work. These are the assumptions. Xi's denote the strength variables having corresponding density and distribution function small f and capital F. Here Y denote the stress variable. Then this is the expression to evaluate this stress strength reliability RSK. Here we are assuming that all the components are experiencing a common stress. Already mentioned that our stress and strength are random variables. So we have to assume a distribution for both these random variables. Here I am assuming exponentiated Gumbel distribution for stress and strength. The density function of exponentiated Gumbel distribution is given as small f of x, and the corresponding distribution function is given in capital F of x. Here, the strength variable xi follows EGD alpha theta. I'm denoting exponentiated Gumbel distribution as EGD, and the stress variable y follows EGD beta theta. So using the expression of RSK, the final expression for stress strength reliability, assuming exponentiated Gumbel distribution as given in equation 1. These are some of the references. Moving to the estimation part, maximum likelihood estimation. Now we have to draw samples from both the distribution EGD alpha theta and the samples ZI denote the random sample from EGD alpha theta and YIs denote the random sample from EGD beta theta. Then log likelihood function for this distribution is given in equation 2. Now we know that we know further procedure taking derivative with respect to the involving parameters alpha, beta and theta. Then these are the normal equation. Then equating this equation to 0 and solving this nonlinear equation, we get the MLEs of alpha, beta and theta, say alpha hat, beta hat and theta hat. Then using the invariance property of MLE, we can find the MLE of stress strength reliability and is given in equation 3. Now we are moving to interval estimation. We are considering two confidence intervals. One is asymptotic confidence interval and the other is bootstrap confidence interval. Asymptotic confidence interval is obtained using the asymptotic behavior of this stress strength reliability. Then for evaluating the asymptotic confidence interval, we have to evaluate the Fisher information matrix. And each term in this Fisher information matrix, and using this theorem, we are evaluating Fisher terms I11, I12, and all these are the terms in the Fisher information matrix. Here psi and psi1 denote digamma and trigamma functions respectively. Then using the equation in equation number 4, we get the asymptotic confidence interval for stress strength reliability RSK. Now moving to bootstrap confidence interval. We have to draw samples from EGD alpha theta, EGD beta theta. Then we have to obtain maximum likelihood estimate. Then using this MLE, we have to draw samples from exponentiated Gumbel distribution. That is, in other words, we can say that we have to draw samples from EGD alpha hat theta hat and EGD beta hat theta hat. Now we evaluate the expression for RSK. Then arranging states in ascending order. Then using equation 7, we get the bootstrap confidence interval. Now Bayesian estimation. In Bayesian estimation, we know that the involving parameters are treated as random variables. So we have to assume distribution to all these random variables. Here, I'm using the prior distribution for alpha is gamma distribution. And for beta also it is gamma. And for theta, it is taken as inverse gamma distribution. Then The density functions are given pi1, pi2, and pi3. Then the joint posterior density function is given in equation 8
You
and
have
is denoted by
3 more
pi
minutes.
star. Hello?
3 more minutes.
Okay, sir. Here we are considering 3 loss functions. Then using these loss functions, we get the base estimators are given in equation 9, 10, and 11. But we cannot solve these expressions explicitly, so we are using MCMC method to generate random numbers from the derived posterior distribution. The posterior density is given in equation 12. So from this posterior density, we can conclude that the conditional posterior density of alpha given theta is given in equation 13, and the conditional posterior density for beta is given in 14. Then conditional posterior density for alpha given theta follows gamma distribution, and beta given theta follows gamma distribution with corresponding parameters. But theta given alpha, beta, so we use MCMC method to derive random samples from the conditional distribution. Here, these are the procedure we used in MCMC method.
Can you conclude?
Then using these samples, we can approximate the estimate as, yes, sir. This is a simulation. Here we are fixing value of S and K. Here we are evaluating stress strain reliability, bias, mean square error, MLE, and Bayesian estimate. We are considering the confidence intervals. For obtaining, we are Bootstrap confidence interval, we are using 1000 iteration. For Bayesian estimate, it is 25,000, and the total iteration in the entire study is 1000. All these are conducted using R package. These are the output. We can, when we observe the table, we can see that as the sample size increases, MSE and magnitude of bias decreases. Then compared to all the confidence interval, the Bootstrap confidence interval has the smaller interval length. Then Bayesian estimation, the estimators derived using Bayesian estimation is better when compared to MLE. And among the 3 estimators, the one obtained under squared error loss function is finer. These are my references. Thank you.
Thank you, Ashlin. And we have no time for questions, so we'll move to second one. Anyway, I have a request to you. Please check your confidence interval. I feel some typo was there. I'm not sure, but please check it.
Sir,
So,
sorry, I can't hear.
Please
Hello?
check your confidence interval. I feel there is a typo. You please check it.
Okay, sir. Sure. Okay. Thank you.
Yeah, our next speaker is Vipin Gupta. I request Vipin Gupta to present this one. Vipin Gupta is here or not? I think Vipin is not here. Is it? Yeah, so we can. Vipin is here? No, I think.
No, sir.
Yeah. What about Yadav? Eddie Yadav?
Yes, sir.
You are here. 1 minute. Because we may not. Yeah. What about Sirisha?
I'm here, sir. I'm there,
Okay.
sir.
Okay. Yeah.
Should I start, sir?
Yes. Please conclude in 10 minutes.
Okay, sir.
Okay. Thank you.
Good evening, everyone. My name is Amit Dev. I did my research under the guidance of Professor S.C. Malik. Research topic is Markov approach for reliability and availability analysis of a 3-unit repairable system.
You can make it to a full screen, maybe F5 or F7 or something like that.
Okay, sir.
Okay, carry on.
Contents includes introduction, abbreviation notations, system description, and some reliability measures. And then graphical and tabular representation are also included with conference and references. Moving ahead to the introduction part. Over the years, the concentration of the reliability engineers is on the development of fault-free systems. But we know that the failures are the ways of life which cannot be ignored completely. Therefore, the prime responsibility of the engineer is to produce a reliable product which can stay in the market for long with the competitors. Thus, the purpose is to develop a reliable system as well as to identify the reliability improvement techniques. We know that availability of the system can be increased using the redundancy in cold standby or in parallel mode. Many research papers have been written by the researchers on the evaluation of reliability characteristics of a system under different configurations, and they also determine so many things, reliability measures with different approaches. L. Dempsey et al. In 2012 carried out analysis for a parallel repairable system with different failure modes. In 2016, James studied the reliability comparative evaluation of active standby versus standby redundancy. In 2017, Clarice et al. Determined the system reliability with the help of Markov technique. In 2020, Sarita et al. Considered the reliability and availability for a non-repairable and repairable system with the help of Markov modeling. Here, our main purpose is on the reliability analysis of a 3 parallel units repairable system using Markov technique. The units are non-identical in nature and they possess the same lifetime distribution. The failed unit is repaired and the system is considered to be failed at the failure of all the units. Some significant reliability characteristics like reliability, MTSF, availability, steady-state availability are obtained in this research work. Christmas glow bulbs is an application of this study. Now moving ahead. So application notations. These are some notations which are used in this research work. Like lambda x represents the failure rate, mu y repair rate, S6 are the states, and T denotes the time. Px is the probability of the system which is in state X at some time T. And A infinity is the steady state availability and RT is the reliability. This is a system which I consider of a repairable system in which 3 units are connected in parallel, which are working simultaneously. As we see in the state S1, there are 3 units are working, and the probability of staying in that state S1 is 1 minus lambda naught del T, and the transition rate from S1 to S2 is lambda naught del T. And the transition rate from repairing from S2 to S1 is mu1 delta T. Similarly, in S2, there are 2 units are working, as 1 unit is already failed. The probability of staying in that state S2 is 1 minus mu1 del T plus lambda 1 del T. The process continue until the failure of all units, which is the state S4. Here O represents the operating state and F represents the failed state. These are some assumptions of my system. The transition rate for the negative exponential distribution. I consider negative exponential distribution because we know that when we do Markov modeling, it follows a memoryless property. And an exponential distribution is a memoryless distribution. And the repair of the failed unit is done immediately at the availability of the repair facility. These are some assumptions. We determine the availability with the help of Chapman-Kolmogorov equations. And these are some boundary conditions. We know that at state S1, the system is at fully reliable. That's why I choose P0 equals to 1. And these are the differential equations after being calculated. So I determine the availability of the system, which is P0T, P1T plus P2T. Here, PQR are the roots of the determinant delta. I solved these with the help of Cramer rule. Now, here we represent the steady state availability, which we know that it is long run availability also. Here A infinity is limit S tending to 0 S A star S, which is here is the given expression. I considered the components as in identical units. Lambda naught is 3 lambda and lambda 1 is 2 lambda. the failure rates and mu1 are the
Your voice
the
is
expression
breaking,
for
sir. Sorry.
availability. Voice is breaking. Hello, audible?
Some disturbance is
Yes,
coming
yes.
from your side, sir.
Hello. Okay, sir.
Yes, carry
Now
on.
I determine the reliability.
Please finish in 4
Reliability of the
minutes,
system.
okay?
Okay, sir.
Okay.
Okay, sir. This is the question type for the reliability. For the MTSF, we know that integration of 0 to infinity of reliability gives us the MTSF. Here, MNO are the roots of the delta, which I determined in the reliability. When the components are taken as identical unit, lambda naught, lambda 1, lambda 2 are the failure rate, and mu3, mu2, mu1 are the repair rate. Now we did the numerical and graphical representation of the expression which we just recently got. As we see from the tabular form, when we increase the failure rate of the system, the availability of the system decreases. But when we increase the repair rate of the system, the availability of the system increases. And with respect to the time, the availability of the system also decreases. Which is shown graphically in this slide. Here it is so that when we increase the availability with the increase of failure rate, we show a decreasing trend of the availability. It's set availability, which is A infinity for long run. When we increase the failure rate of the system, the availability of the system decreases. And similarly, for when we increase the repair rate of the system, the availability of the system increases. In this slide, for the reliability, it also gives the same results. Like when we increase the failure rate or when we increase the time, the reliability of the system decreases. But when we increase the repair rate of the system, the reliability of the system increases. Shown graphically in this slide. Yes, ma'am. Well, in this table, when we increase the failure rate of the system, the MTSF of the system decreases. And while increasing the repair rate, we saw that the MTSF of the system increases. From these tabular and numerical graphs, from these graphs and tables, we concluded that the system is more reliable and available to use whenever we increase the repair rate of the systems. There are some references. Thank you so much.
Okay, thank you, Yadav. Nice one. Actually, I like it because I work in reliability analysis. Anyway, this Anuradha is here. Hello.
Not joined, sir.
Anuradha is here. Or?
Not joined, sir.
Not joined. Okay. 1 minute. Okay then. This Hafiz is here. Well, I just wanted to.
Sir, I'm Sirisha, sir.
Yeah, I know. No. Actually, I am asking if some more people are there, I can give some more time.
Okay,
Means
sir.
10 minutes or 12 minutes, 2 minutes I can give more. That's why I'm asking. What about intake of alarm? Okay, Sirisha, you can present your.
Can you see my screen, sir?
Yeah, something you can see. Yeah.
Am I audible, sir?
Yes, carry on.
I'm Dr. G. Sirisha, Assistant Professor from Department of Statistics, University College of Science, Osmania University. Today, I'll be presenting on reliability properties of compound Rayleigh lifetime distribution 2.
Madam, make it full screen, ma'am.
Can you see, sir, now? Is it
You
clear?
can make it little smaller, I think.
Full screen, ma'am. Keep it in full screen mode. Showing
It
only
is
how.
in full screen.
Then you put a control minus, then it may reduce, I think. Yeah, now
I'm doing.
Yeah.
Before you are connected, ma'am.
Okay, sir.
If you can reduce little bit, then it will be more clear. Yeah, now it's okay, I think.
Okay, sir. I'll be speaking on reliability properties of compound Rayleigh lifetime distribution 2. These are the assumptions which I have used to build up this model. The first assumption is the basic lifetime distribution T of a product is assumed to be Rayleigh distribution with the density small f of t given by t into alpha power minus 2 e power minus half t by alpha whole square, where t lies between 0 to infinity. And the other assumption is the measurable quality characteristic X of the product is assumed to be normally distributed with mean mu and variance sigma square. And sigma is known to us according to the modified control limits. Here I am using 3 concepts to develop this model. One is modified control limits, the other is reliability concepts I'll be using, and I'm using compound distributions concept as well to build this model. According to modified control limits, I need to first supply U and L, the lower and upper specification limits prescribed by the designing department. Based on the observation of the production process over time, let us assume that the U minus L, this difference is greater than 6 sigma, implies that the process is capable of producing better products, meeting the specifications. Under this framework, let us assume that the manufacturer decides to relax certain constraints on the process, which can be in terms of material, raw material, or manpower, or skilled manpower, or machinery. The third assumption used is this fine-tuning, this relaxation in the constraints will lead to a shift in mu, which is according to triangular distribution in the range mu L to mu U. And this mu L and mu U are obtained according to modified control limits as mu U equal to U minus 3 sigma and mu L is L plus 3 sigma. And it is observed that the greater the shift in mu, the greater will be the deviation from the process mean mu naught. And due to this variation, the expected lifetime, as the variation increases, the expected lifetime will drop down. This concept is used in the next, building up the next assumption. The increase in the absolute deviation of mu from mu naught results in an increase in the reciprocal reverse relation in the reciprocal root of 1 by 2 by pi into 1 by alpha of the expected lifetime. And the same is projected in this mathematical form. Root 2 by pi into 1 by alpha is equal to C plus mu equal to V, where C and M are greater than 0. And U is nothing but the absolute deviation of mu from mu naught. Properties of CRLD2. These properties I have projected in the last ISPS conference. Those properties are, if T is the lifetime of the product, of the new product, which is produced according to this relaxation, then the density of this lifetime, capital D, which is, I'm calling it as F star of T, is given to be as 2 into M delta power minus 2 integral C to C plus M delta into M delta plus C minus V into T pi V square by 2 into E power minus half T square V square pi by 2 dV, where T lies between 0 to infinity, V lies between C and C plus M delta. This same PDF, a probability density function, F star of T, can also be expressed in terms of incomplete gamma distribution function. F star T in terms of incomplete gamma can be given in this form, where omega 1 is nothing but T square C square pi 4 power minus 1. Omega 2 is T square into C plus M delta square pi 4 power minus 1. The other property is the expected lifetime, which is given to be as E star T, which is 2 into M delta power minus 2 into C plus M delta log of M delta C inverse minus M delta. And this, as we have already seen, this expected lifetime of the new model will be definitely less than that of the original Rayleigh distribution. And variance of this new lifetime capital T is V star of T, which is 8 into M delta power minus 2 pi inverse into M delta C inverse minus log of 1 plus M delta C inverse minus 4 times of M delta power minus 4 into C plus M delta into log of 1 plus M delta C inverse minus M delta whole square. Distribution function F star of T is given in the form of 1 minus of 2 into C plus M delta power minus 2 into T power minus 1 pi power minus half into gamma of half omega 1 minus gamma of half
You are not audible, madam.
We can't hear anything now.
2 plus 4 times of M delta power minus 2 T power minus 1 into gamma of 1 omega function derived to be as R star of T is equal to 2 into C plus M delta into M delta power minus 2 T power minus 1 pi power minus half gamma of half omega 1 minus gamma of half omega 2 plus 4 times of M delta power minus 2 T power minus 2 pi power minus 1 gamma of 1 omega 1 minus gamma of 1 omega 2. Proof follows from the definition. Definition of reliability is R star of T equal to 1
I
minus
think
of
you can skip
distribution
the
function.
proof because we don't have much
Yes,
time.
yes. Just if you subtract, you will be getting the expression. In the same way, the hazard function, the hazard rate of the distribution, H star of T is derived to be as this expression, 4 times of C plus M delta into M delta power minus 2, T power minus 2, pi power minus half, gamma of 3 by 2, comma omega 1 minus gamma of 3 by 2 omega 2, minus 8 times M delta power minus 2, T power minus 3, pi power minus 1, gamma of 2 comma omega 1 minus gamma of 2 comma omega 2, whole thing divided by 2 into C plus M delta power minus 2 T power minus 1 pi power minus half gamma of half omega 1 minus gamma of half omega 2 minus 4 times of M delta T power minus 2 pi power minus 1 gamma of 1 comma omega 1 minus gamma of 1 comma omega 2. And proof again in terms of the definition, H star of T is equal to density by reliability. Already I have given the expressions for density and reliability. The same if I incorporate here, I'll be getting this expression, which I am calling as 1.11. Now, in the same way, the cumulative hazard function, capital H star of T is nothing but integral of small h star, just integrating. And this integration is not in a, this function is not in the closed form. So integral could not be evaluated, but I can represent this integral in terms of incomplete gamma integrals. And given the parameter values, we can obtain by using Abrowitz and Stuyvesant's tables. I have evaluated H star of T values. This is the example which I have used to illustrate these reliability expressions. According to the example, U is equal to 75, L is 73, and mu naught is 74.001. Estimated sigma is 0.00989. And definitely in the, according to this example, U minus L will be greater than 6 into the sigma value, which I have quoted here. Modified control limits, if I use, I'll be getting mu U to be in this form, mu L to be as 73.02967. Delta is mu U minus mu L by 2, which I have obtained to be as 0.97033. This mu U and mu L I have obtained by using U minus 3 sigma and U plus, L plus 3 sigma. Now I have obtained, in 2 minutes? Yes, sir. I have obtained R star and H star values. I have compared them with the original Rayleigh R and H values in this table by considering different C and M values. We can see that the values of R star and R almost they are similar, very small variation between them. In the same way, H star and H. The same graphically I have represented here, reliability function and hazard function. You can see just like your Rally distribution, even this distribution has IFR failure rate distribution. You can see the curves, both Rally, standard conventional Rally and this new model. Very small variation is there. So I can conclude that any manufacturer, if likes to relax the condition based on the modified control concepts, then he can do it. But at the same time, he should maintain transparency to take care of the customer's interest. And so accordingly, the manufacturer should project this new distribution rather than the conventional distribution. These are my references. Thank you, sir.
Thank you, Sirisha, for your presentation. We will straight away move to the next one. Anuradha is here. I think she's here.
Yeah, yes, sir.
Yeah, please present.
Is my screen visible?
Yes, we can make it into full screen. Control L. Control L will do. Not working?
No, sir.
Oh, then.
Okay, no problem.
PDF,
Continue.
Madam, full screen, madam.
Good afternoon, everybody. Myself Anuradha, and topic of my presentation is profit analysis of 2 out of 3 G system with priority to repair and conditional failure of service.
Madam, excuse me. Madam, make that window big. Upstairs. Go up.
These are the content of my presentation. First slide is about introduction, next abbreviation and notation, then assumption and fair distribution of the stochastic model, then some reliability calculations for some reliability measures, and then profit analysis and application of the old model. Introduction. In the era of growing industrialization, it has become mandatory to produce high reliable products with the latest technology, maintaining the optimal balance with manufacturing cost. As a result of which, the system designers and reliability engineers have bound by the industries to identify the best possible performance improving techniques so that their system may have a great market value. With the advent of new technology, we are now in a position to enjoy the uninterrupted services of the systems. On the other hand, the customer prefer cost-friendly systems with least snags during their use. Stochastic modeling has led us to do things differently and efficiently with the help of better reliability techniques and including provision of redundancy, proper repair policies, good quality products, and proper contingency plannings. The K out of N system is a one kind of a partial redundancy and has been widely used in repairable system to increase the availability and hence the profit of the system. There are several studies which has been conducted for particular type of K out of N systems under common assumption that system can work for a long time without requiring any maintenance. This assumption seems unrealistic as continuous operation and aging of operable systems reduce their performance, efficiency, reliability, and hence safety. Malik and Bhardwaj have analyzed 2 out of 3 redundant systems with general repair and waiting time distribution. Kishan and Kumar in 2009 studied a parallel system with preventive maintenance. Different repair policies in case of server failure have been studied by R. Downie. The system of parallel units can be made more profitable by making replacement of the failed unit in case server failure to get its repair in a fixed time. Malik and Gitanjali in 2012 obtained reliability measures of such parallel systems. The concept of priority has been introduced by Malik and Nandal. They have developed various reliability models for standby systems. Malik et al. In 2030 have analyzed a parallel system with the concept of priority to repair over preventive maintenance. Yang et al. In 2015 have discussed the reliability analysis of load sharing layout of a system considering component degradation. However, the idea of priority to repair over preventive maintenance along with the failure of service facility has not been introduced while analyzing system reliability model for more than 2 or 3 reliable components, identical components. Discussing a 3-unit identical system named as 2 out of 3G system. Initially in the system, all the units are operative and 2 units are mandatory to be good for proper functioning of the system. The system undergoes for preventive maintenance with an arbitrary rate in order to restore the efficiency of the working units. There is a single service facility which performs the preventive maintenance as well as repair of the units. The server facility may fail and therefore undergoes for treatment to restore the efficiency to carry out the remaining repair activities. There has been given priority to repair over preventive maintenance. The semi-Markov process and regenerative point techniques have been used to analyze the system model. There are some abbreviations and notations used in the next slides. There are the assumption and state description. There are 3 identical units. All the units are initially operative and 2 units are required to be good for proper functioning. The system undergoes for preventive maintenance with an arbitrary rate. There is a single service facility which performs preventive maintenance as well as repair of the unit. The service facility may fail and may go under treatment. There is a provision of priority to repair. This is the state transition diagram. The description of the state transition diagram shown in previous slide. S node is the initial state in which all the 3 units are in operation. S1 is the second state in which there are 2 units which are in operation and 1 unit which was failed after state 0 is under repair. State S2. There are 2 units which are in operation and 1 unit is under preventive maintenance. In the same way, all the other states have been defined. These are some reliability characteristics of the system model. First is the MTSF and transition probability. The transition probabilities have been shown in the slide. Mean sojourn time and mean time to system. The reliability equations and MTSF equations are given in the form of these equations. Here phi IT is the CDF of first passage time from regenerative state SI to a failed state. These equations have been solved using Laplace transform and Kramer-Rao rule. These are the equations for availability. Busy period of the server due to repair, busy period of the server due to preventive maintenance. This is the expected number of repairs of the unit, expected number of preventive maintenance of the unit, expected number of visits of the server in the long run. These are some reliability characteristics on the basis of which we have calculated profit of the system. The profit of the system model can be obtained in the using the equation given below. PC is equal to C naught A naught minus C1 BP, where C naught C1 C1 are the costs. C naught is the revenue per unit cost per unit time. C1 is the cost per unit time the service facility is busy for repair. In the same way, C2 and C3 are defined. BP0T, these are the steady state busy period of the server due to repair, busy period of the server due to preventive maintenance and visits of the server. Particular values of the profit have been calculated using by taking the numerical values of C0, C1, C2 and C3 and exponential failure rate of the busy period of repair due to busy period of the server due to repair, preventive maintenance and visit of the server. This is the real life application of the described model. The real life application of a 2 out of 3G system can be visualized in flame detection circuit for a toxic waste incinerator. Burning of toxic waste, especially waste produced in chemical factories, medical laboratories, produce a lot of harmful and lethal gases. To neutralize the toxicity of these kind of gases, intense heat of fire is required. The principle behind the working of an incinerator is as long as the flame is maintained in the incinerator, it is safe to introduce the waste inside the chamber to get it neutralized. If the flame is extinguished or is not sufficient to neutralize the toxic gas produced, it would be very harmful to continue to inject waste into the combustion chamber, as it would exit the exhaust unneutralized and may cause a health threat to anyone in close proximity. Therefore,
can you conclude in 2 minutes?
Yeah, so this is the pictorial presentation of the toxic incinerator. Graphical presentation of mean time to system failure versus preventive maintenance rate, availability versus preventive maintenance rate. The conclusion of the stochastic model of a 2 out of 3 G system is that the study reveals that there is a decline in these measures with the increase of rate by which a unit undergoes for preventive maintenance, and preventive maintenance, failure rate of the unit, and service facility. For all these 3 rates, the availability, MTSF, and profit increases. However, if we increase the repair rate or preventive maintenance rate of the units, the availability, MTSF, and profit goes on increasing. Thus, a system like 2 out of 3 G system can be made more profitable to use by increasing the preventive maintenance rate of the unit in case priority to repair over preventive maintenance is given. These are some references.
Thank you, Anuradha, for your presentation. We will go to the next speaker. I think this Pradeepa Vidyakumari is not present. What about alarm? Intake of alarm? Then who is the next one? Is there any other people? Rajesh Kumar or Rajesh Kumar is here. So anybody is here present? Yeah, Rajesh.
Good afternoon, sir.
Reliability variation analysis.
I'm Rajesh Kumar.
Yeah.
I'm doing PhD under the supervision of Professor S.C. Malik, and my topic is reliability variation analysis of series parallel system of M&I order with addition and removal of subsystems.
Sir, presentation mode, sir.
Can you make it?
Yes, sir. I'm audible.
Yeah, you can make it
okay.
Full mode.
Okay, sir. Okay, sir. Okay, sir. Thank you, sir. Contents, introductions, notations, and abbreviations, system description, reliability variation, illustrations, discussion, and conclusion, applications and references.
Can you make it a presentation mode? Full screen, full screen. Just press F5.
Okay, sir. Yes, sir.
F5, F5.
F5.
Yeah. Otherwise,
notations and abbreviations. Could I start? May I start, sir?
Sorry, sir. 1 minute. Down one button is there, sir. Click on that button, full screen now. Window button is there. No? You click on that, sir.
This is the PDF file?
No, yes, sir. Yes, the PDF file, sir.
Then Control L. You put Control L.
One second.
Control L.
Control L.
This is PPT, sir, not PDF.
Control L, sir.
No, PPT, sometimes they save it as PDF.
Okay.
Whether it is a PDF or PPT.
PPT, sir. PPT, sir.
Then F5 will F5 or F7. Just to check it.
F5 or F7.
Yeah, F7. Fine.
So now it's okay, sir.
It's okay
Yes,
now.
yes.
Okay, sir. Okay, sir. Thank you, sir. The reliability of the transformed system and also the variation in reliability in both systems has been obtained. The expression for variation in reliability of the transformed system have been derived from exponential failure of components. The variation in the reliability for a 4-3 order series parallel system has been obtained in order to see the usefulness of the methodology described in this work. A linear regression model to this variation in reliability of the systems derived from 4-3 order series parallel system by augmenting X 1 to 3 and deleting Y 1 to 3 subsystem is fitted to examine the goodness of fit on the basis of R square and adjusted R square for particular value of the failure rate of components and operating time T. The variation in reliability with respect to the value of X and Y for a fixed value of failure rate lambda has been shown graphically. The real life application of this present work has been discussed. Notation and abbreviations. RFST, reliability of initial system, RTST, reliability of transfer system. And this is the main system description. Here we consider MNI order series parallel system in which M subsystem are connected in series and each subsystem has NI I1 to M number of components connected in parallel as shown in figure here. This is my system. These are subsystems C1, C2, C11, C12, C1, NI minus 1, C1. This is first subsystem connected in series and each subsystem had components connected in parallel. Then the reliability of the initial system is product J1 to M, 1 minus product Ji 1 to Nj, 1 minus Pij. Now, reliability variations can have two cases. Case number first, let X series parallel subsystem is augmented or added in the initial system. The augmented subsystems Nj, Jm plus 1, M plus 2, M plus X can be represented by the following figure. The reliability of the augmented subsystem is RAT product by J equal to M plus 1 to M plus X into 1 minus product I1 to Nj, 1 minus Pij T. Now the transfer system has M plus X subsystems connected in series and each subsystem has Ni I1 to M plus X components are connected in parallel. The block diagram of the transfer system is shown by the following figure. Now the reliability of the transfer system is given by RTST. Now we shall the relative variation due to augmented system. This is the calculations and my final result is delta RT. Reliability of the initial system, relative variation, reliability of the initial system and minus reliability of the transfer system, and the result will be RTST, RS, IST, RAT. The reliability of the transfer system, reliability of the initial system into reliability of the augmented system. When Y series parallel subsystem are deleted from initial system, the block diagram for the deleted subsystem is shown in figure 4. And for this, reliability of the deleted system is product J equal to M minus Y plus 1 to M into 1 minus product I1 to Nj, 1 minus Pij into T. When we delete M minus Y parallel subsystem connected in series having components Ni, I1 to 3 M minus Y from initial system, then the transfer system can be represented by following figure 5. And the reliability of this is product J1 to M minus Y into 1 minus product Y1 to Nj, 1 minus Pij T. The variation of the reliability and the final result is is delta R1T, the reliability of the initial system, into unreliability of the deleted system divided by reliability of the deleted system. So reliability of the transfer system, last reliability of the initial system divided by reliability of the deleted system. Illustrations. Let's consider an initial series parallel system of order 4-3, order having 4 subsystems connected in series, and each subsystem having 3 identical components, I12, 1, 2, 3, connected in parallel. Suppose failure time of the components follows exponential distribution with failure rate lambda. The diagram can be represented by the following figure 8. This is a figure. Now we shall discuss the reliability variation of initial system after augmenting and deleting subsystem, assuming that all components are identical with exponential failure law as follows. If time to failure of components are exponential distribution distributed with failure rate lambda, then from equation first, these are the results. If x 1, 2, 3 parallel subsystems are connected in series in initial system, then the reliability variation in the initial system due to augmentation of subsystem can be obtained as numericals and graphical representation. Table first. Reliability variation versus failure rate of components in initial system. Failure rate of components lambda dash in augmented system and a number of added subsystems are explained by numerically and graphically in the following manners. These are value of lambda, these are value of lambda dash, and these are added subsystem 1, 2, and 3. This is the graphical representation reliability variation versus failure rate. As we see, as we go on increasing the subsystem, then reliability variation must go on increasing. Regression analysis. To fit the regression model on variation in reliability. To check the effect of reliability variations after augmenting subsystem in the original system with failure rate lambda in the exponential failure law, the linear regression model has been fitted for the data for arbitrary value of the parameters. Here, reliability variation taken as the response variable and the failure rate lambda augmented subsystem X are predictor variables. MS Excel is used to analyze the regression model. We have the following results. Regression analysis. To fit the regression model on variation in reliability. To check the effect of reliability variation after augmenting subsystem in the original system with failure rate lambda in the exponential failure law, the linear regression model has been fitted for the data for arbitrary value of the parameters. Here, reliability variation taken as the response variable and failure rate lambda augmented subsystem X are predictor variable. MS Excel is used to analyze the regression model. We have the following results. Table 2. Let 5 parallel subsystems connected in series are deleted from the initial system having components failure rate lambda and with time t equal to 5, and the results are represented by numerically and graphically in the following manners. Here we delete subsystem 1, 2, and 3, and these are lambda values 0.5, 1, 1.5, and these are the graphical representation. Fit the regression model on variation of reliability. To check the effect of reliability variation after deleted subsystem in the original system with failure rate lambda in the exponential failure law, the linear regression model has been fitted for the data or arbitrary value of parameters. Here, reliability variation taken as response variable and failure rate lambda deleted subsystem are a predictor variable. MS Excel is used to analyze the regression model. Here, the value of R square and adjusted R square are 0.81 and 0.70. These are much high values, and we can see that model is a good fit.
One question here in
Yes,
the
sir.
response variable, this reliability variation can be negative.
Response variable can be no, sir.
Then what? How can you use this regression? I don't know.
Has been used by MS Excel, sir.
Yeah, that I understood, but I think it is better to use log of that reliability variation so that you can make the response variability into real line.
Sorry, sir, please. Again, sir. No, sir, we have used MS Excel.
Carry on, I will tell you at the end.
Okay, sir.
Continue, please
Okay, like
continue.
after deleting the subsystem. Okay, sir. Okay, sir. After this, we get R square 0.181 and adjusted R square 0.700916, which provides a good fit for the fitted model. Variation system had constant lambda after augmenting and deleting parallel subsystem in the original system of MNI order. Method is described that can be used for other systems like series, parallel series. Also, an attempt has been made to fit the linear regression model for reliability variation by taking 4 subsystems, and each subsystem had 3 identical components. The value of R square and adjusted R square are also calculated to check for the best fit of regression model for the data. It has been noticed that after adding or deleting subsystem in the original system, the reliability variation will go on increasing in both cases. Also, the regression model for reliability variation in augmenting system can be considered very good fit, since the value of R square and adjusted R square are very high. Also, in deleting subsystem, the value of R square and adjusted R square is satisfactory and can be predicted a good model. To show the effect clearly, the results are given first and second. Applications. The application of this work can be used in solar panel system, since the use of solars in the present time is more useful because of no environment pollution and no coal requirement. Actually, the solar panel system is made of solar cells having capacity of 0.5 volts. These are connected in series. When solar panels are connected in series, current will remain same, but voltage of all series connection will be added. So when more voltage is required, then additional solar panels can be added. When the requirement of the voltage is not much, then we may decrease the solar panels. Solar panels
Thank you.
Okay, sir. Thank you, sir.
Thank
you. Thank you. Sir.
Any question? Is this a predictor variable can be negative or both are positive? One is failure rate, so it is a positive. What is the other one?
Yes, sir.
This failure rate you have 2 predictors. What are the predictors?
Sir,
regression.
added subsystem X.
Okay. So that is both are positive. That's why you are not have any problem in regression. Otherwise, normally, if you are dealing with the lifetime, normally consider log T normally. Because
Okay,
if you wanted to incorporate predictors which has negative value, one has to consider log T. So thank you for your presentation.
Okay, sir. Thank you, sir.
Any other presentation is there? Anybody is there? Otherwise, I can ask some questions to some of the people. Okay, let us. Anyway, do you want to ask anybody? Want to ask any question? Okay. So let us then conclude it. Thank you all for presenting your work in this ISPS conference.
Thank you, Professor Sudesh Kumar Kattumanil, sir, for chairing the session.
480-21164. 480-21164.
So we will continue
Now
after
he is
the
in the
lunch.
state. You can start now.
Hello. Just to reconfirm, we are in Hall B.
Yeah, I think you are at the right place.
Okay, thank you. The presentation by the students was very good.
Yeah, sure. But I mean, if you see the dissertation, I think there was some, you are able to separate. But the presentation, I think one above the other.
Yeah, the content was different. One could judge them differently, but the presentation, they were so confident.
Yeah.
Very neat, no hiccup.
Well prepared.
Very well prepared. The teachers must have grilled them and got the best people to do it. So I was very impressed.
And you know, in one of the team is from Bangalore University. There is no government faculty there. The whole department is run by a set of guest lecturers.
The biostatistics team?
People have retired, but there was no new appointment.
And the other team was from which department?
They are from a medical college. There is Yenapoya Medical College.
The one who talked about vaccines.
The middle one, second one.
Yeah.
No, I think the last team. Sorry, last team.
Yeah, the one they talked about vaccines.
First one was from Madras Christian College.
Okay. But they were very good. I was very impressed with
all are good.
Yeah.
So, Dr. Patracharilu, Professor
Sir, you are ready, sir? Yeah, another 2 minutes is there?
Yeah, I'm confirming. Parameswara Pandit is online. If he wants, he can introduce, start the session if he wishes.
But
okay. What is the final?
No, Parameswara.
Yeah, I am here, but I may have to go to the other session early.
What?
Okay, then fine.
This is Bhattacharya, sir, Professor Parameswara Pandit, sir.
I am here.
Just
I am here, but I may have to go to other session in the middle.
Yeah. So can I request the Balakrishna, sir, in place of your session to chair the AC? Now I request Professor N. Balakrishna, President ISPS and Senior Professor, Department of Statistics, question University of Science and Technology, question Kerala, to occupy the chair and introduce the speaker and please conduct the session.
Okay, fine. Okay, Isha madam, you are ready, right?
Yeah, I'm ready. Yeah.
Okay.
I need to be given the screen sharing facility.
Yeah, I'll just tell you.
Okay.
So, good afternoon and welcome to the first session after lunch. So, this session is going to be, Dr. Isha Diwan is going to speak on this, in this session. Dr. Isha Diwan is a professor of statistics at Indian Statistical Institute, New Delhi. She is an active researcher in reliability, surveillance, and the related areas. Currently, Dr. Isha is also the president of IAEC India chapter. And this is a special endowment lecture in the memory of Professor Y.C. Narasimulu, who was a professor of statistics at SU University, Tirupati. In fact, I had several occasions to interact with Professor Narasimulu. He had visited our department several times for conferences and the examination work. So he was a very nice person. Whenever he visited us, he used to bring prasadam from Tirupati, that is laddu, and he used to wish us whenever he comes here. So unfortunately, he is not with us now. So with this fond memory, we'll start the session. Now I invite Professor Isha Madam to give her lecture on tests for independence of failure time and cause of failure in competing risk model. Over to Isha, madam.
I request the host to let me share the screen.
Yeah, please
You can
allow
share,
to share the
ma'am. You
screen,
can
please.
share, ma'am.
So thank you to the organizers for giving me an opportunity to give this talk. And a correction, my term as IASA President for India chapter is over. Now Dr. Devjeet from Pfizer takes over.
Okay.
Yeah, so please note that. Yeah. So I'm going to talk about tests for independence. Is the screen visible?
Yeah.
Yeah. And just one request, there are some issues with the network at our end. So if it trips, please give me a call. I'll reconnect. Thank you.
Okay.
So this is a topic which I've been working over for the last 2 decades. My earliest work was with Professor Deshpande and Sangeeta. And over the years, I have worked with Shankaran and Shri Devi on this topic. And the major part of the current presentation is joint work with Sudhish and Shri Devi. So I would like to thank both of them for this. So I will start the talk with an outline of what competing risks is. Then talk about tests for independence when both random variables of interest are continuous. Then look at the competing risk setup where the failure time is continuous and causes are discrete. But most of the emphasis would be on the case when both failure time and causes of failure are discrete. We'll introduce the test statistic, talk about some simulation results, and list quite a few open problems in this area. So the simplest example of a competing risk setup comes from a series system in reliability. We have a series system with n IID components. When it fails, we can observe the system failure time, which would be the minimum of the component lifelines. And also we'll be able to identify the unit which led to the system failure. So the data arises as a bivariate random variable, the failure time and the cause of failure. In survival studies, we know time of death of individuals, and the cause of death could be heart attack, COVID, cancer, etc. So again, we have information on a bivariate random variable. Another illustration is number of months spent in unemployment registry, and finally the job which the individual attains. So it has applications outside reliability and survival analysis. So when you have a pair of random variables x and y, both continuous, something which is done in the undergraduate program in statistics is you assume that xy has a bivariate normal distribution with correlation coefficient rho. Given a random sample from this population, you can test for independence of x and y by testing that rho is 0 on the basis of the sample correlation coefficient. So everyone must be familiar with this procedure. If one drops the bivariate normality assumption, one can look at several non-parametric tests for testing for independence. Two very popular ones are Candle-Storr and Spearman's rho. We'll talk more about Candle-Storr. So given n pairs of random variables x's and y's, Candle-Storr is defined as 1 over NC2, number of concordances minus the number of discordances. So what is concordance and what is discordance? Given two pairs xi, yi and xj, yj, we say that the pairs are concordant if xi is less than xj and yi is less than yj, or xi greater than xj and yi is greater than yj. So the pairs are concordant if x's and y's are ordered in the similar manner. And they are discordant if xi is greater than xj and yi is less than yj, or conversely, xi is less than xj and yi greater than yj. So they are discordant if the order of x's and y's, when you compare the pairs, is reversed. One can easily show that under independence for large n, root n times tau has a normal distribution with mean 0 and variance 4 by n. So in the competing risk setup, the very general framework which has been popular, the failure time is assumed to be a continuous random variable, but the causes of failure are discrete. So one could have k causes of failure, and these are mutually exclusive and exhaustive. So one needs to look at modifications to Candle's law to look for tests of independence in this case. Some general notations. T is the failure time. There are k causes of failure. Ft is the distribution function of the failure time. St is its survival function. Something new comes up in the theory of competing risks, and that is the subdistribution function. It's the joint probability of T and C, and denoted by probability T less than equal to T, C equal to J. Note that at T equal to infinity, FJT is not 1. So it is not a distribution function, but a subdistribution function. The subdensity function is the derivative of the subdistribution function with respect to T. It's very easy to see that the distribution function f is the sum of k subdistribution functions. Similarly, the density function of the failure time is the sum of k subdensity functions. Then analogous to the failure rate, in competing risk setup, we have cause-specific failure rates denoted by lambda jt, which is the ratio of the subdensity function fjt to the survival function. The interpretation is the same. It's the probability of instantaneous failure, but due to the jth cause. And the failure time of T can be written as sum of these cause-specific hazard rates. So T and C are dependent random variables. And it's very important to look at the nature of independence or dependence between these two variables which come up naturally in competing risks. If T and C are independent, we have the subdistribution function fjt can be written as the product of marginals. So it is equal to probability C equal to J ft for all T. So if they are independent, one can handle the failure time separately and the cause of failure separately. An important characterization which has been looked by several authors, the time to failure and cause of failure are independent if and only if the cause-specific hazard rate functions are proportional. So this is the result given in Crowder's book. So our first paper with Professor Deshpande and Sangeeta was for the continuous case when k is 2. The null hypothesis was T and C are independent, but we looked at several alternatives. The general one being that the two are not independent. but specific alternatives of bivariate dependence in terms of PQD, right tail increasing and left tail decreasing. So the idea explored for the test for independence was a generalization of Kendall's law. So define a function psi as 1 if Ti is greater than Tj, Ci is 1, Cj is 0, or Ti is less than Tj, Ci is 0, Cj is 1. So we are talking about concordance between the pair Ti-Ci and Tj-Cj. So if there is concordance, psi takes value 1. If there is discordance, it takes value -1 and 0 otherwise. We construct a U statistic based on Ut, which is 1 over NC2, summation of the kernel psi t over, there's a typo, it's over I less than j less than equal to n. And we looked at asymptotic distribution of this statistic. But when failure time is discrete, one cannot use the above statistic, and the asymptotic normality worked out in that paper does not go through. But before that, let's look at some examples where failure time is discrete. The number of pages printed by a Xeroxing machine before it fails. This would be a discrete random variables. Number of days a patient stayed in a hospital after a surgery is again a discrete random variable. Number of miles a vehicle runs before its first breakdown is discrete. If a device is monitored only once per time period, and the random variable of interest is the number of time periods successfully completed prior to its failure, we are again in the discrete case. So in the discrete setup, new notations have to be introduced. The cause-specific hazard rate lambda jt is defined as probability t equal to t, c equal to j, given t greater than equal to t, which is the ratio of the subdensity function fjt to the survival function s at time t minus 1. And the subdensity function fjt now is probability t equal to t, c equal to j. As before, the failure rate of lambda is the sum of the k cause-specific hazard rates. Ft and St, the distribution function and survival function, are defined similarly. And we need to bring up pi j, which is probability that the failure is due to cause j. So the null hypothesis is T and C are independent. And we are looking at the general alternative that T and C are not independent. Under independence, the subdistribution function fjt is the product of the two marginals, pi j and ft. And this idea is exploited. So consider the measure of departure delta, which is summation j varying from 1 to k fjt minus pi j ft square with the weight ft over pi j and summed over all t. Under the null hypothesis, delta is 0 and it is positive under the alternative hypothesis. Remember, we are looking at a very general alternative of lack of independence. So that is why we need to square fjt minus pi j ft square. Little bit of calculations, and one can write delta as summation over j 1 over pi j summation over t fj square t ft minus summation over t f square t ft. Then one can easily see that summation over t fj square t ft can be written as probability maximum T1, T2 less than equal to T3 and C1 equal to C2 is equal to J. So both the failures of T1 and T2 are due to the jth cause. We know nothing about the failure of the third component. And summation over T, F square T, Ft is probability maximum T1, T2 is less than equal to T3. And clearly here, the index J has no role to play. So the cause of failure does not come into picture. Then we exploit the theory of U statistics. We look at a U statistic estimator for the first probability, which is maximum T1, T2 less than equal to T3 with C1, C2 equal to J. This is not a symmetric thing. So we symmetrize the kernel. Psi is 1 under 3 different choices of the triplet T1, C1, T2, C2, T3, C3, and 0 otherwise. And for the second probability, maximum T1, T2 less than equal to T3, we look at a symmetric function psi2, whose expectation is the probability, and define a U statistic estimator, which is 1 over NC3 summation over I less than R less than L less than equal to N of the psi2 function. So once we have this, the test statistic is easy to write. Delta hat is summation j varying from 1 to k, u1j over pi hat j minus u2, where pi hat j is a consistent estimator of probability c equal to j. So it is just the proportion of times the system fails due to the jth cause. Asymptotic distributions are easy to handle using the theory of U statistics. So as n tends to infinity, root n u1j minus delta 1j is distributed as a normal random variable with mean 0 and variance 9 times sigma square 1j. But unfortunately, one cannot write a nice expression for the variance even under the null hypothesis. You can see that the CDF F, the probability mass function small f, indicator C1 equal to j, pi j, all come up in the expression. So this is definitely not distribution free. Similarly, the second U statistic, properly normalized, converges to a normal random variable with mean 0 and variance 9 times sigma 2 square, which under H0 again is a function of capital F and small f. So again, the variances will depend on the underlying setup. So more calculations, one can show that under the null hypothesis, square root n, capital U is the vector now consisting of U1, U2, UK, and U1j up to so on U1k and U2, minus its expectation, converges in distribution to multivariate normal with mean vector 0. The variance covariance matrix is again messy, not distribution free. The expressions are pretty lengthy, so I'm not writing it here on the slides. But under the null hypothesis, as n tends to infinity, root n delta hat, the measure of interest, converges in distribution to normal with mean 0 and variance sigma naught square, which is the quadratic form A transpose sigma A, where A is 1 over pi 1 up to 1 over pi k minus 1 transpose. Since the variance term depends on the unknown distribution functions, even under the null hypothesis, as well as pi j's, we look at a consistent estimator of sigma naught square and reject the null hypothesis for large values of the normalized version, root n delta hat over sigma naught hat. So how does the test perform? We look at a model which was earlier proposed by Sangeeta and me by looking at some competing risks problems. So we have k equal to 2. The subdistribution function of the first cause is written as pi1 times FAT, and that of the second cause F2t is Ft minus pi1 FAT. So this is kind of a combination or bringing in the layman type of alternatives to the competing risk setup. For this model to be valid, A must lie between 1 and 2, and pi1 must be between 0 and half. It's easy to check that T and C are independent when A is 1. For simulation studies, we look at two different distribution functions. One is the discrete geometric distribution, Ft given by 1 minus p to the power t, where p lies between 1. We look at p equal to 0.1, 0.3, 0.5, and 0.7. The other is the discrete version of the Weibull distribution, which is Ft is 1 minus p to the power t to the power beta. P lies between 0, 1. Beta is positive. We look at p equal to 0.3 in the tables. We've tried it for other p's, and beta equal to 0.8, 1.2, 1.5, and 2. For beta equal to 1, we end up with the discrete geometric distribution. Pi1 is taken as half. The discrete geometric is kind of a discrete counterpart of the exponential distribution satisfying the lack of memory property. So that was the reason for looking at this. Weibull is a very popular distribution studied in survival analysis. So we looked at its discrete counterpart. So here are the results for empirical power when the underlying distribution is geometric. So A equal to 1 corresponds to the empirical size of the test. These are the values that have been highlighted on the screen. You can see that for n equal to 25, the test is very conservative, with empirical size ranging between 0.03 and 0.04. But empirical size kind of stabilizes for n equal to 75 and 100. But given the empirical size, whether it's less than 0.05 or closer to 0.05 for the 5% or 0.01 for the 1%, we see that powers are pretty good. So for A equal to 1.2, the empirical size was 0.035 for P1. And for the same sample size, the power is 0.348. So the test seems to perform well and is able to pick up alternatives even close to the null. Similar conclusions were seen for the Weibull distribution, with empirical size kind of stabilizing at n equal to 100. And then the powers were good. So the conclusions were the proposed test has achieved its size for a sample size of n equal to 100. But even for small sample sizes, the proposed test has good power. When A equal to 2, significantly away from the null, the power approaches to 1 for almost all choices of parameters considered here. So the test performs pretty well for the families of distributions that we have looked at. So next we illustrated it on a real data set. The data consists of drug-exposed pregnancies discussed in a paper by Byersman et al. In 2011. The data consisted of 1186 pregnant women. The pregnancy outcomes are classified as induced abortion, live birth, and spontaneous abortion. So here K was 3. There were 3 different categories to which the data could be split. And luckily, we had information on all times as well as all categorizations for all women. So complete information was available. Number of weeks from conception to any of the 3 events is considered as the lifetime. So when we looked at the data, 58 had induced abortion, 1016 gave live births, and the remaining 112 experienced spontaneous abortion. The statistic delta hat is obtained as 0.0359. We obtained the critical values of the regions also using Bootstrap. So we rejected the null hypothesis that time to failure and cause of failure are independent. And we found out that cumulative incidence functions due to induced abortion and spontaneous abortion are dominating in earlier weeks of pregnancy, which is pretty intuitive. I think I can skip this, how we found the critical points. I'll list down several open problems in the discrete case. We have not been able to extend this test statistic to the case when failure times are censored, so that needs to be done. One reason for that is that in the continuous case, we have tools given by Datta et al., where they weigh the observed failures by inverse of the Kaplan-Meier estimator and then work out the asymptotic theory. We do not have any counterpart to Datta's theory for discrete random variables. For the continuous case, there are lots of people who use the counting process approach for testing purpose, for looking at the asymptosis of the test. Shankaran, Shridevi, and I have used this approach when we looked at categorical data, but we need a corresponding counterpart for the discrete case. As mentioned while talking about the real data, luckily we had information on causes of failure for all subjects in the study. But what do you do if the causes of failure are missing for some of the individuals? We need to look at that scenario. All these cases have been handled for the continuous failure time case. Then, as mentioned earlier, we had developed tests for independence against specific dependencies like PQD, right tail increasing, left tail decreasing for the continuous case. We have yet to do that for the case when the failure time is a discrete random variable. And there's one thing which I would like to emphasize. Even though the entire terminology has been brought up in the sense of competing risks, the proposed test for independence can be used to study the nature of dependence between 2 discrete random variables, where one random variable takes finite number of distinct values, while the other can take infinitely many values. So the applications of these results are many. And there's one practical concern which somebody would have noticed. While defining the statistic, we looked at t equal to 1 to infinity. So how do you do it in real life? In real life, we are going only up to the maximum observed failure time, and that takes care of the theoretical part. So I think I'll stop here. Thank you and look forward to comments.
Okay. So very good and very well in time. I think you spoke very nicely so that you are able to keep the people awake even after the lunch. So now I invite comments and suggestions from the participants. I could follow everything, but I don't think I am able to ask any questions because I have not done any work in this area. Professor, will you speak?
was perfectly timed.
Sorry?
I think there was an internet trip, but it was just after I finished. I didn't miss anything. So any questions, comments? I would be happy to listen to them.
Do you think there was some interruption in between? I think
Was there? There was
just
an interruption at the
just
end.
after
I
we
know.
finished?
Yeah, there was an interruption. That's why
Oh,
I
I
said
see.
it happened
That means
just at the last minute.
I spoke a lot of things in between, but nobody could listen to that.
Okay, okay. So there was an interruption. So
Oh,
I
I see.
rejoined.
No, what I was talking is when you finished on time as well as and you spoke very well. I think even after a heavy lunch, people are able to be awake. So such a way, nicely you have presented.
So any questions?
I think I expected some questions from Professor BLSP.
Professor Prakash, or also any suggestions for the counting process approach?
Professor Balakrishna said, no, I have stopped in this area for quite some time back. So,
okay. Because I remember attending your classes on inference for stochastic processes.
Right.
But they were all continuous time.
Yeah,
so
most of the time, because the discrete one involves a lot of combinatorics.
Yes,
So that's why
we
I
need to
think.
venture into this area, but need to learn lot many things.
Yeah,
so.
sure. Yeah. Well, it was a nice talk, Isha. So very nice.
Okay, I think there are not many people also around. So if there are no
Yeah,
more questions, so on behalf of the organizers and ISPS, I thank Professor Isha Diwan for her nice and very well-planned talk. Thank you, madam. Thank you very much.
Thank you. Okay then.
Bye.
Thank you, Professor Balakrishna sir, for taking the chair and with a short period of notice. Now, the next session will be starting within 3 minutes because the Professor S.C. Malik sir and Professor Hanagal sir is already there in the another session. The talk is going on within few minutes. So the talk will be over in that and they will join in this session.
Yeah, I will be moving to the session or this PhD in that the research paper competition.
Okay, sir.
Okay, thank you.
Okay.
Professor David, sir, shall we start, sir?
Yeah, we can start.
Okay. Now, it is my honor to introduce Professor David D. Hanagal Garu, Professor and Head Department of Statistics, Vishwakarma University. He was elected as
I am
the
already introduced by Professor Malik. There is no need to introduce. Already introduced by Professor Malik. Just now.
Okay, sir.
In a hall. In a hall.
Okay, sir. I request you to occupy the chair and introduce the speaker, sir.
Okay, I'll introduce the speaker. Okay.
Thank you, sir.
Professor Malik, Professor of Statistics, MD University, Rohtak. He is a head of the department also, and President of Indian Association for Reliability and Statistics. He is the Chief Editor of International Journal of Statistics and Reliability Engineering. Research specialization, reliability theory, modeling, sampling theory, and applied statistics. Teaching interest, statistical methods, probability theory, applied statistics, optimization techniques, real and complex analysis, measure theory, stochastic process, reliability theory, and modeling. He has more than 30 years experience and teaching and research both together. Administrative experience also he has as a NSS coordinator, proctor, chief warden, and other things, HOD, MD University, and other things. He has supervised more than 45 PhD theses and 30 MPhil dissertations, 112 MSc projects. He has more than 200 research publications, authored 3 books. He has participated in more than 100 conferences, workshops at national and international level. He has visited several countries like USA, Portugal, UK, Germany, Singapore, Canada, several countries he has visited. He is a member of several academic bodies also, PG Board of Studies, Central University, Haryana, member of expert committee, and DST for the period of 3 years. Academic Council of University, elected member, Executive Council, MD University, elected member, University Court, UGC Advisory Committee, UG, PG, Board of Studies, member of selection committees in various universities in India. Okay, Professor Malik, your talk is, the title of the talk is the Markov approach for evaluation of reliability measures of repairable systems. Now over to Professor Malik.
Yes, thank you very much, Professor David Engel, for a brief, nice introduction about me. Really, I'm very grateful to you. And I'm happy that you are again chairing this session. So I skip out to the PPTs. Yes, visible?
Yeah, visible.
Okay, thank you, sir.
You can make full screen view.
Yeah, yes, I'm making. Yes, now it is okay. Okay.
Yeah, full screen.
So first, I'm very thankful to the organizers for giving a chance to say something about the Markov approach for evaluation of reliability measures of repairable systems. This is a very important work so far as the research in this area is concerned, because every young researcher needs to go through the basic concepts of Markov approach. Although we have several techniques to determine reliability measures of repairable systems. So we have two types of systems, repairable and non-repairable systems. So I'm going to discuss here only the repairable systems and some reliability measures of repairable systems. We have several techniques to determine the measures. One technique is very famous, that is a Markov approach. Then we have semi-Markov approach. All these are stochastic models, stochastic processes. And we sometimes need to evaluate reliability of the system without making much changes in the structure of the components. So here we are considering repairable systems of 4 identical units. First, there is a need to understand reliability. Reliability measures means the measurements that can be used to assess the performance of any systems, may be repairable or non-repairable. Reliability means the probability of no failure of the system. But we cannot avoid all these things because the failures are inevitable. We cannot stop the failure of the system because every system can have some deterioration with respect to the time. So we cannot avoid completely the failure of the system. But this does not mean the system cannot be made reliable for use. That we can improve the system performance with the help of some techniques, or we can assess the reliability with the help of some specific methods, well-known methods. So here the target is only to provide a methodology to how to determine the reliability measures of repairable system with the use of Markov approach. If we see the Balaguru Swami book, in that book, how the technique is discussed, Markov approach technique discussed only for 2-unit systems. 2-unit system, and reliability is determined. Here we are undertaking a very complex system of 4 identical, initially 4 non-identical units. Then we consider the case of identical units. Then we assess the reliability. So the basic purpose is to provide the methodology how to determine reliability measures with the help of Markov approach in case the system has more than 2 units. So here we discuss first reliability, then mean time to system failure, then availability of the system by Markov approach. So we shall cover the following through this talk. Now, over the years, the concentration of the reliability engineers, you might be knowing that, on the development of the fault-free system. Everyone is interested to purchase or buy such systems which can have a least number of troubles or snacks. But the failures are the ways of life. We cannot avoid it completely. Now, we are today surviving in the age of fast-growing technology. In the fast-growing technology, everyone is interested to purchase or to remain in the competition and interested in to buy a good system. That good system means that the system which has less number of troubles, or that can suit us in all respects. But suitability purely depends on the quality and the reliability of the system. Therefore, the prime responsibility of the engineer is only to produce, not only to produce the reliable system, but also to develop the system by keeping in with the cost constraints also. On the other hand, the purpose of the system designers and reliability engineers only to develop the reliability system, but also to see the to determine the reliability techniques which can be used to improve the performance of the systems. Over the years, we have several reliability improvement techniques. Now we are in a position to enjoy good systems which can prove itself up to the expectations of the users. So some reliability improvement techniques we have: the provision of the spare units. We sometimes need to provide a spare unit in order to improve the longevity of the operation. So sometimes we need the proper structure of the components, because the structure of the components also plays an important role to improve the performance of the system. Although we have several types of structures: series structure, parallel structure, mixed mode structure, in case of series parallel and non-parallel series systems. So it is also proved that parallel structure of the components is better than that of series structure so far as reliability is concerned. All these researches we have today in the literature. So the component structure plays an important role to improve the performance of the system. And another thing is that sometimes we need to develop or to consider the appropriate maintenance policies that can be used to improve the performance. And sometimes we need to take the high quality components for the development of a good system. So it is clearly proved that the availability of the system can be improved with the help of the redundancy techniques. Redundancy technique means the provision of the spare units in the system. The redundancy may be in terms of cold standby, maybe in terms of warm standby, maybe in terms of parallel mode of the units. So also today we have a lot of literature available in the direction, but in most of the cases, the system reliability has been assessed by, or the system models, hazard models, we can consider developed by considering the regional point approach or semi-Markov approach. But the use of Markov approach is not has been considered much more in case of determining the reliability and availability of the systems of more than two components. So here we have some references which we have been motivated to develop the Markov approach for more than 2 units of the system repairable systems. So in this direction, we have Il Devesi et al. 2012 analyzed a parallel repairable system with the cold standby consideration. James compared reliability of active and standby redundant systems. Calariciel et al. In 2017 used Markov technique to analyze the system reliability. Sita et al. In 2020 evaluated the reliability of 4-unit non-repairable system. They did not consider the repairable system, but they considered only the 4-unit non-repairable system by assuming at least 2, 3, or 4 models must be operated for the successful operation of the system. Here we in this talk is interested to provide a methodology to determine the reliability of parallel system of 4 non-identical units using Markov approach. So the failure we are considering, the failure and repair times of the units, simply we are considering here the case of a constant nature. That is, we are considering here a negative exponential distribution for the failure time as well as for the repair time. And then we develop the Chapman-Kolmogorov equations to obtain the reliability. Then with the help of the Laplace transfer technique, we in a position to determine the reliability as well as the mean time to system failure and availability. Then we see the behavior of these measures visits to different parameters related to the failure time, repair time, and operating time. Then we have to produce the application part of the work. So these abbreviations and notations we have used to develop the system Markov graph. So we are considering here lambda is the failure rate, x in the specs, that is the failure rate at the state x. The state may be 0 state, that is the initial state, operating state, starting state, first state, second state, 3 state, and 4th state. So we have total 5 states in general, because we are considering here 4 units, non-identical units in the system. So we have a total number of 5 possible states. Then we accordingly, we take the repair rate for the repair of the yth units. The units may be first, second, because we are considering 4 number of units. Then we represent Sx the states, possible states. So we have total possible states in the Markov graph are 5. T is the time, Tx is the probability that system is in state X at time T. A infinity, we are considering the availability of the system in the long run, the reliability and the mean time to system failure. You might be knowing that mean time to system failure means the expected time before the system completely failure. First we determine the mean time to system failure, then we first we determine the reliability, then we determine the mean time to system failure. Because you might be knowing that there is a relationship between MTSF and reliability. Yes, now this is the system description. What we consider here, we are considering here a system of repairable system of 4 non-identical units. This is a Markov graph for all possible states. Here we have the first state S1. In this state, all the 4 units are working simultaneously in parallel mode. Then there may be chances of failure of either of the units. If there is a failure, then definitely we still have 3 units to work in simultaneously. So, but we are here considering the consolidated failure rate of the entire system, that is lambda naught. But our interest is to assess the transitions in the time t plus delta t, because we are observing the system at time t, and we need to assess the transition in a smaller possible time delta t. So the probability that there is a failure of 1 unit from state this to this is lambda naught delta t, and after repair the system will become again the same as in the initial state. because here three units are working and all these three units are non-identical, but one failed unit is under repair. After repair, it will be considered as good, so it will be again at the initial state. But at this stage, because we have the possibility that the one unit may also fail out of these three units, so the failure rate here will be different, because in the initial stage all the four units were working. Now at this stage only three units are working, so there is a difference of failure rate. So we are considering at this stage the failure rate is lambda 1. So the probability that there is a failure of one unit out of these three is the probability is lambda 1 delta t. Similarly, we can have all these five states. One state is the last state will be failed state. When we consider the failed state will be only when all the four units failed completely. Then this is the fifth one state, which is not being seen in the PPTs. So O is the operating state, F is the failed. So this is the Markov graph on the basis of the assumptions. So here we determine the reliability, availability of this system. So the transition rates, we have already discussed that we are considering here negative exponential distribution. Repair rate, again, the repair of the failed unit is done immediately. This is our assumption at the availability of the repair facility. Then it means, what does it mean? We can modify it, again the Markov graph, if we make some changes in the assumptions. But here we are considering the immediate arrival of the repair facility. The system is completely considered as failed at the failure of all the units. So we have already discussed that first state, second state, third state, fourth state, and fifth state. Then with the help of Chapman-Kolmogorov equation, so we have the following expression of Chapman-Kolmogorov equation for determining the availability. So P naught T delta T plus delta T means that is the probability that the system will be in the initial state in time T plus delta T. Here there may be the possibility either the system will remain in the initial state up to time T, or there may be a failure. So then the probability is P naught T into 1 minus, or there will be no failure in time delta T, or there is a failure in time T, then there is a need to repair it. Because our interest is to determine the probability that the system will remain operable, will be in the first state in time T plus delta T. So we can, by considering all the possibilities, so we can have this expression. Similarly for the state 1, state 2, state 3, and state 4. So we have all these Chapman-Kolmogorov equations. Then by taking the limit delta T tends to 0, then we have the following differential equations. So we are in a position to determine the expression into the differential equation. We have P naught dash T, that is the derivative of P naught dash T, is equal to P naught T minus lambda naught plus P1 T mu1. Similarly, we have the expression for the others in terms of the differential equations. Now, all these now taking because we have the best stable method for determining the solution of the differential equation with the help of Laplace transform technique. It is the beauty of the Laplace transform to provide a solution of the differential equations. So with the help of the Laplace transform, we can have the following expressions in terms of the Laplace transform, but all these expressions are subject to the boundary conditions. So the boundary conditions for this is P naught 0 is 1, P1 0 is 0, P2 0 is 0, P3 0 is 0. What does it mean? P0 0 means that at the probability that the system at the initial stage will be operable. Yes, fully operable. We cannot assume that at the initial stage system will be in the failed condition. So its probability is 1. Similarly, we can have the boundary conditions for the other possible states. So the system equations will be up by putting all these values, putting s equal to 0. So we can have again a system of linear equations. After solving these, we have the availability. Availability means the probability that the system is available for use at time t. And this is only the possibility that if the system remains in state, original state, first state, second state, and third state, then we can say that the system is available for use, because last state, the system is not found available for use because all units have already been failed. So we need to determine the probability for determine the availability, that is P0T, P1T plus P2T plus P3T, or we can write it because sum of the probabilities of all the positives is 1. So by using the concept of probability, so it means we need only to determine 1 minus P4T. And this is the expression after solving the previous equation, the linear equations, we can have the following expression for the availability. But sometimes we need to determine the availability in the long run. For the availability of the long run, we need to take the limit t tends to infinity. So the probability in the long run means this will be the values. And here we have the expressions in terms of the roots, because we need to determine the availability. Then we shall make use of the expressions of Chapman-Kolmogorov equations to determine the reliability also. What is difference between reliability and availability? In case of availability, both are probability. Reliability is also probability. Availability is also probability. But the thing is that in case of availability, the concept of repair is there. But in case of reliability, no need to get the things, failed things, to get in operation again, because reliability means probability that the system is working in a particular period, available, or that there is no failure of the system in a particular period. And but the probability that if the system is available for use, may because of the after failure getting of the repair or otherwise. So there is a difference between reliability and availability. So here we need to no need to consider the repair of the state 4, because but in case of availability, we need to get the things again in operation. That's why the difference is in the P4T expression. There is a difference. So after taking the Laplace transform, use of Laplace transform technique, we can have and using the boundary conditions, we have the following expression for the reliability. Reliability means P0T plus P1T plus P2T plus P3T. That is before complete failure. So up to here, the system is working. So we need to consider the sum of the probabilities of these possible states. So P0T, P1T, P2T, P3. Or again, this is equal to this, but the expression is this. Here, okay. So O, M, and R are these expressions which we need to determine with the help of the computers. So meantime, the system value of the system is, you might be knowing that, simply the integral of the reliability from 0 to infinity. So we can determine MTS of S. So here, M and OP are the roots of the delta. Delta R is this expression. So these are the roots. So after putting all these, now we need to assess what will be the effect of different parameters on availability and reliability of the system of such type of nature. So here we are considering only the hypothetical data. We are not considering any first-hand data. We are considering only the hypothetical data. For this hypothetical data, here we are assessing the effect of failure rate. If suppose the failure rate is like this, 0.01, 0.02, 0.03, 0.04, like this, and if we take the repair rate is 0.01 and operating time is 10 hours or 10 days or 10 minutes, then we have the behavior of availability as, if we increase the failure rate, then there is a decline in the availability of the failure, there is a decline in the availability as usual, as all these things are theoretically available in the literature also. But with if we increase the repair rate, then certainly there is an increase in the availability. So what we conclude that if we, on the other thing, if we increase the operating time also, then there is a decline in the availability. What we conclude with the help of this data, that the availability of the system decreases with the increase of the failure rate and with the increase of the operating time. But there is a change, improvement in positive direction in availability with the increase of the repair rate. So somehow we can maintain the availability of the system by adjusting the repair rate and failure rate. But so far as failure rate is concerned, we cannot control the failure rate of the system. So, but we can provide the repair facility as we wish. So the repair rate we can consider, or the operating time we can have. We can fix the operating time also to make the system more available to use accordingly. So this is the graphical representation on the basis of the figures available in the data available in the previous table. So far this is the another situation no need to explain, already discussed these things. This is the availability which to repeat. Then we assess the reliability. If we see the reliability variation, that is which to the failure rate, again we see that reliability again declines. Here, in case of failure, suppose failure rate is 0.01, then and with respect to the repair rate 0.01, then the reliability of the system is 0.999. But if we change the repair rate from 0.01 to 0.03, then it becomes more. And but if we increase the failure rate, if there is an increase in the failure rate, then the reliability certainly decreases. So the same behavior, there is we can observe that the behavior of the availability and reliability, which to the failure rate, which to the repair rate, which to operating time, more or less same, but having different values for the reliability and availability. Yes, we can see it through graphs also. Similarly, the mean time to system failure. The mean time to system failure, that is the expected time before the system completely failure, and that has been evaluated in terms of the reliability, because MTSM is simply the integral of the reliability for the long run period, for the long period. So if we see the mean time to system failure, the behavior of the mean time to system failure is same as that of reliability and availability. So we can draw the same conclusion on the basis of the hypothetical data. So similarly, we have this. Now, what we conclude that, suppose we have a system of 4 identical or non-identical units, then purpose is how we can make this system more reliable and available to use. It can only be controlled with the help of our repair facilities. So there is a need to provide appropriate repair facilities to make the system more reliable to use, because we cannot have the control over the failure rates. So proper repair facilities are required, and there are several other techniques to solve such type of model, but here we are considering only the Markovian approach to determine the reliability. If we are in a position, and then we have several other techniques also that can be used to determine the reliability and availability of the system. But in this talk, we are only focusing on the Markov approach. So this work has a very beautiful application in the area of mining, cryptocurrency, queuing models, and electric circuits. So we have many other application areas, but cryptocurrency case can be considered the good application of such type of work. So here we have 4 types of units which are working in parallel. So sometimes we need to translate the data or store the data in more than 1 unit or more than 2 units. In that situation, we need to keep the systems in parallel mode with the help of two or more components. In that situation, the work has beautiful applications. So these are the references which we have used to develop the system or to develop the theory. So yes, further we can have the work in this direction. Actually, the cost benefit is still to touch in this direction with the help of Markov approach. So cost benefit analysis needs to be carried out for repairable system by considering core standby and parallelency using Markov approach. This area is still to touch. The concept of fuzzy reliability still is to be addressed using Markov approach. So we are planning to work in this direction also. So if there is any scholar who is interested to do in this direction, then need to read some references that I already discussed with you. So that's all about this talk. If there is any question, you are free to discuss with me. And thank you, all of you, for showing patience. Thank you. Yes, Professor.
Okay. Any questions or any queries, comments from the audience?
Yeah.
Any comments from the audience? If there are no comments or queries from the audience, I thank Professor, we all thank Professor Malik for the very interesting talk delivered today, and it's very useful to all the audience in the reliability. He's very expertise in the reliability, theory and other things. And I thank for his wonderful talk. Let us thank Professor Malik.
Thank you, sir. Thank you for sharing time. Thank you. Please.
Okay, my work is over to, now the platform is over to the organizers.
Thank you, Professor David Hanagal, sir, for chairing the session. Thank you.
Thank you.
Professor Sutish Kumar Katumanil, sir, shall we start the session, sir?
Yes,
Professor,
yes,
yes,
you
sir.
can start.
Yes, sir.
Sorry, I am attending another function. But it is fine. Correct. Okay.
Now I request you to occupy the chair and conduct the contributed paper session in the stipulated time, sir. Thank you.
Yeah. Okay, thank you. So we have again 10 papers, 44 to 53. All this. Just to see, first 2-3 people are present, then accordingly we will proceed. Okay.
Okay, sir.
So Joshi is here. Subhashri Joshi. Hello.
Sir, she is not going to present the paper today.
Who is? She is not presenting.
Yes, sir. I have sent a message to you, sir. Three members are
Who
not.
is Shilpa is there? Shilpa Subhash?
No, sir. She is also not presenting.
Then who is there?
Third person, Pradeep Veeramani.
Huh?
Mr. Pradeep, sir. Next.
Okay, Pradeepa Veerakumari. Okay, so then we have 2 people are not there. Okay, you can take around 12 to 15 minutes. Okay, maximum. Okay, please go ahead.
Hello.
Pradeepa.
She is also not joined, sir. Still waiting.
Huh?
She is not joined yet, sir. And the organizer, sir, I'm speaking to you.
Then who is there?
Sir, I am there, Sushil Malik.
Sushil Malik is there.
Sushil Malik is here?
Yes, sir.
Yes, sir.
Can you do now?
Sir.
Hello?
Yes, sir.
Is it possible to present now?
Yes, sir, it is possible.
Okay, then you do, please. Eh?
Okay.
Yeah, you please present. Sushil Malik, okay? Yeah, thank you. You can take around 12 to 15 minutes.
Okay, sir.
Make it a full screen, F7, I think. F7. Yeah.
Shall I start?
Yeah. Yes.
Okay, sir. My name is Sushil Malik, research scholar in Department of Statistics, MD University, Rohtak. Today I'm here to present my research paper on the entitled Logic Diagram Technique for Reliability Evaluation of a Non-Series Parallel System with Arbitrary Failure Probability Distributions. The contents of my presentation. First, we have talk about introduction, abbreviation notations, system description, reliability of the system, reliability measures for arbitrary probability distribution. Here we take Weibull and gamma distribution, then conclusion and references. Now, as we all know that we are in the era of fast-growing technology, where the demand for reliable products has gained much attention among consumer and producers. Reliability plays a vital role to aware the engineers for adopting proper repair policies and effective structural design of the products. And we all know that system reliability can be enhanced by either using the good quality components or by arranging the components in best configurations. There are many system structures having frequently used by the system designers, such as series system, series parallel system, parallel series systems, and mixed mode systems. In 1994, Balaguswamy described the series and parallel systems, and he also revealed that the parallel system is better than that of the series system so far as reliability is concerned. In 2013, Levitin et al. Studied a series parallel system and evaluated its reliability using the random failure propagation time concept. Now, there are also non-series parallel systems in the environment. They are systems in which the components are neither arranged in parallel and non in series. Balaguswamy in 1984 determined the reliability of 5-component non-series parallel system using the logic diagram technique. In 1982, Chaudhary et al. Evaluated the fuzzy reliability of non-series parallel network Allowed et al. In 2018 evaluated the reliability of a non-series parallel system of 6 components with Weibull-Failure laws. In 2020, Malik et al. Obtained the reliability of a non-series parallel system of 7 components with Weibull-Failure laws. Here they have considered a single component through which the maximum flow of information is allowed to pass. But we all know there are systems in which 2 parallel components are required for passing the maximum flow of information, not only to improve the reliability of the system, but also to provide alternative path or its use in emergency case. Hence, we in this research use the logic diagram technique to determine the reliability of a non-series parallel system of 7 components. Here in the system, we have assumed 2 components are connected in parallel and the other 5 components are connected in series in 2 different parallel paths. And the maximum flow of information has been passed through these 2 parallel components. Now, and the system is converted into simple parallel series system by using the logic diagram technique. Here we also use make the use of Weibull and gamma distributions for the random variables associated with the failure rate of the components. The reliability measures are evaluated using simple probability laws. The arbitrary values of parameters, scale and shape associated with the different failure times are considered to examine the behavior of the reliability measures. The real-life application of the study can be utilized in electronic systems such as cell phones and computers, motherboards. Now the abbreviations and notations. Here Sj is a jth component in the system. RUT reliability of the system at time t. RIT reliability of the ith path at time t. Small rjt reliability of jth component at time t. M represents the number of parallel paths. S represents the total number of components in the system. T is operating time. MTSF mean time to system failure. Vj is skill parameter of the jth component. Kj is the shape parameter and Rj is the rate parameter of the jth component. Now, this is a system we have taken. This is a 7 component non-series parallel system in which 3 components are arranged in series S1, S2, S3, and other 2 components S4 and S5 are also arranged in series. And there are 2 components S6 and S7 which are arranged in parallel in the middle of the system. And maximum flow of information is passed through these 2 parallel paths. And then we convert this non-series parallel system into the simple parallel series system by using the logic diagram technique. We obtain the logic diagram for the non-series parallel system as shown in the figure 2. Here we have shown that the components find place more than once in the paths. So we discard those paths which are dominated by other paths as they have no effect on the reliability of the system. And after this, we have the reduced logic diagram, which is shown in figure 3. And we have finally made the use of this reduced logic diagram to obtain the reliability of the system. Now, the reliability of the system is given by the expressions. Let RJT be the reliability of jth component, where j is from 1 to 7, and Ri, because there are 7 components in the system, Rit is the reliability of the ith path, as there we have 8 paths in the reduced logic diagram. Then the reliability of different paths is given in the equation 1 to 8, and the reliability system is given equation 9 with the help of the formula we obtained for parallel series system. After simplification, the reliability is comes out to be in the form of equation 11. Now, if we consider that all the components are identical, then the reliability of the system is obtained with the help is given in the equation 12. Now, we have considered that the components hazard rate follows Weibull distribution. So the reliability of the jth component is given as RJT, which is equal to e raised to power minus t power t by vj e power kj, where j is from 1 to 7, as shown in equation 13, where v and k are the scale and shape parameter. Now, if the components are identical, then reliability is given with the help of equation 14, and the MTSF is given with the help of 15. Now, the numerical and graphical representations. Here we have seen as we increase the scale parameter of v, the reliability of the system increases, and as we increase the shape parameter, the system decreases, and also when we increase the time, the reliability of the system decreases. Also shown in the graph. Now, when we talk about MTSF, when we increase the scale parameter, similarly as the reliability, here also the MTSF increases with the increasing scale parameter, and with the increasing shape parameter, the MTSF decreases. We also shown in figure 5. Now, we have considered gamma distribution. Suppose the components hazard rate follows gamma distribution, then the reliability of the jth component is given as shown in equation 16. Here, S is the total number of components. So the reliability for S equal to 7 components is shown in equation 17. And if the components are identical, then the reliability of the system is shown in equation with the help of equation 18, and the MTSF is given with the help of equation 19. Numerical and graphical representations. Here, as we increase the rate parameter B, the reliability of the system decreases, and as we increase the time, the reliability of the system decreases. Which is also shown with the help of figure 6. And about MTSF, here as we increase the rate parameter B, the MTSF of the system decreases, which is also shown with the help of the graph. So we conclude that the reliability of the system increases with the increase of scale parameter, while it decreases with the increase of shape parameter in case of Weber distribution, while the reliability of system decreases with the increase of scale parameter in the case of gamma distribution. These are references I have used in the study. Hello. I'm audible?
Sir.
Yes.
Yes, sir.
Hello.
Hello.
Audible.
Yes, sir.
Done. Any question?
Anuresh Krishna, please withdraw. Please
No.
withdraw.
Yeah. Hello.
Yes, sir.
Who?
Next, Sweetie, sir. Sweetie, sir.
Shilpa is here now? Or Pratibha?
Next is Sweetie, sir.
Srijita. Sweetie.
Yes, sir.
What about Bharat?
Yes, yes, Professor Sudesh, I am here.
Sir, I am here.
Oh, sorry, Neeraj. Okay. So then we start with Sweetie.
Yes, sir.
Okay. Yeah. Why I am asking some more people so that they can take some more time. That's why.
Okay, sir.
Normally we have only 10 minutes, but now we don't have some people, so you can take some more minute if you need it. Okay.
Good evening, everyone. Myself, Sweetie Kadyan from Department of Statistics, MD University, Rohtak, Haryana. I have carried out this research work under the supervision of Professor S.C. Malik, and my title is Stochastic Analysis of a Non-Identical Repairable System with Operational Priority to Simultaneously Working Units. And these are the contents. First of all, the introduction section, and then system description and transition diagram. Then some reliability measures are carried out for the system, and then some numerical and graphical presentations are made, and then a profit comparison is made with an older paper, and then conclusion and references. So pollution and limited natural resources are most prominent problems whenever we are go with some new technologies, but always we find that there are lack of energy, and natural resources are so less in quantity now that we have to consider some energies that can be unlimited, like solar energy, wind energy. So using solar energy is considered the best solution to these problems, and in this direction many governments are taking major steps so that people are using more and more solar products. And some researchers have also carried out reliability of different solar products, like Newman and Peter obtained reliability of solar microgrids. Jordan studied reliability of solar panels and concluded that solar power is an unreliable energy source because it is intermittent, inefficient, and cannot meet and cannot meet electricity demand. As we know that we can't completely rely on solar panels, especially in some areas where there is very less temperatures, which are at high altitude. So we for electricity needs. So many researchers have come out with a solution that solar products should be used with a combination of hydro or wind energy, and there are many studies on reliability of such hybrid systems, but as we see that all the reliability studies are conducted only for government level, or the whose planning level, where a complete town is getting their electricity from solar energy and other sources of energy. But we can see that more and more people are using solar panels on their personal level too, so it is very important to check if such kind of setup is also reliable or not. So so check the reliability of such a setup. Here we are using a model in which initially solar panels are activated, but there is also a solution. Whenever the solar panels are not available, then we can use the electricity which is supplied by government through transformer. So you can visualize this situation by this diagram, where there are two solar panels, a factory is using these, and also it is having electricity from transformer. So if we talk about reliability literature only, then we can see that simultaneous working units are not considered by very much scholars. Only one or two papers are available, and even in those cases the priority is given to the single unit or transformer, but no one has given priority to those simultaneous working units. So here in this paper we are giving priority to simultaneous working units. Also, there is a paper by Kadyan et al. 2020, where they have given operational priority to the transformer, that single unit. So we are making comparison so that we can know that which priority would be better to use. So this is the system description and notations. A 3-unit non-identical repairable system is used where there are total 3 units, one type 1 unit and 2 type 2 units. In type 1 unit, we are taking as transformer, and in type 2 units, we are taking solar panels. Type 1 unit is more efficient than type 2 unit in terms of failure and efficiency. Solar panels are given operational priority as it can lead to very good economic situation if they are more and more functional. So we are giving the operational priority to solar panels. So initially solar panels are providing power to the factory or home, whatever it is, and none of the solar panels is individually capable of bearing the load of the power of the factory. So whenever any of the solar panels fails, the factory has to use the power supply from transformer, and the factory has no power if any of the solar panels and transformer fail altogether. There is a single repairman who calls on immediately whenever any type of units fails, and the units are in pristine condition after every repair. The states of the system can be described as follows. We will go with this transition diagram. So here we can see that in the initial state as note, we can see that both the solar panels, the type 2 units are active, and the type 1 unit is in standby, cold standby. So whenever any of the you can see the transition from S0 to S1. So whenever any one of the type 1 units or solar panels fail, the type 2 units fail, the type 1 unit become operative, and this goes under repair, and the second one is waiting for operation. So that, whenever this gets repaired, as we have given operational priority to type 2 units or solar panels, so whenever it gets repaired, it goes back to initial state. Similarly, the other states. So these are some of the notations used. We can see that the failure rate of type 2 units is lambda 1, and failure rate of type 1 unit is lambda, and repair rate of type 2 unit is G1T, and repair rate of type 1 unit is GT. And these are some other notations used in the study. This is the transition probabilities and mean solution times. We can simply find it using simple probabilistic class. This is the reliability and MTSF of the system that is under study. This is the availability of the study in steady state. These are the expected number of repairs for type 1 unit, and these are the expected number of repairs to repair type 2 unit. These are the expected number of visits of the server. This is the busy period analysis of the server due to repair. And finally, the profit analysis. The only availability gives us profit. So this is the availability into K naught, which is the revenue generated per unit time whenever the system is in up state, and these are the cost involved in the system. So here we are giving the taking only two costs, which is the busy period of the server and the cost paid per visit. We can also take different kind of profit analysis where we are not giving the server busy period, and these other like we are giving per repair, so these can be taken into account. So this is the graphical and numerical presentation of these reliability measures, and of course to have graphical and numerical presentation, we have to take some numerical values of these all parameters. So for this we have taken GT and G1T, which are the repair distributions, as alpha e raised to the power minus alpha t, which is negative exponential distributions with the different parameters alpha and beta. And value of lambda is taken as 0.01 to 0.019 because in India transformer failure rate is given 12% to 17% as per the study conducted by Singh and Singh, and the value of lambda is taken as 0.001 because solar panels failure rate is given as 0.05% by Jordan and Coates, but it is the very old paper, and many studies are indicating that the newer solar panels are having more and more cracks. So we have taken the value 0.001. Also other values of the other parameters are taken values same as the Kadyan et al, because we have to perform a comparative study so that we can know that which of the strategy is better to give a priority to type 1 unit or type 2 units. So this is the numerical presentation of MTSF. Here we can see that whenever the failure rate of type 1 unit is increasing, the MTSF is decreasing. And here there is a typo error. It must be beta, not alpha. Because in MTSF, alpha is not involved. Alpha is actually the repair rate of type 1 unit, and MTSF encounters only the time for the failure for the first time, and when the first failure of the system occurred, there was no repair of type 1 unit, so it's only beta and it's just a type error. That's why alpha is not there in this table, so alpha won't affect MTSF of the system. And if we see that when we increase the repair rate of type 2 unit, then there is a huge increment in the MTSF, and when we increase the failure rate of type 2 unit, then the MTSF is almost half. So we can see this from this graph also. So we can say that failure rate of type 2 unit is the parameter which is affecting this MTSF of the system very very much. And here is the availability, and if we check the availability of the system, then again the same pattern is following whenever alpha and beta, which are repair rates of type 1 and type 2 units. So whenever we increase them, the availability is increasing, and whenever we are increasing the failure rate of type 1 or type 2 units, there is a decline in availability of the system. So again, we can see this by graph 2.
Can you conclude within 2 minutes, 1 or 2 minutes?
Yes, sir, for sure. Similar is the case for profit. And when we compare this profit with the system that is studied by Kadyan et al., then we found that our system where we were giving the priority to simultaneous working units is more profitable than that one where the priority was given to type 1 unit. So this is the conclusion we can say from this study. We can conclude that a system with simultaneous working with priority to simultaneous working units will be more profitable as compared to that one which is not giving priority to it or giving priority to type 1 unit. Also, it is suggested that we should use less prone to failure type 2 units or solar panels so that we can have a high reliability and availability of the system. These are some of the references used in the study. Thank you.
Thank you. Thank you. Anybody have any question? Okay. So hello, Neeraj, not present.
Professor?
Yes.
Actually, Neeraj is one of my students.
Yeah, yeah, I
want
know.
to present the paper on behalf of Neeraj. This is MS Barak.
Oh, you are presenting?
Ji.
Okay, okay, then fine. Okay. So 12 to 15 minutes maximum. Okay. Thank you.
Okay, sir. Okay.
Yeah, yeah. Actually, our presentation is 10 minutes, but some of them are not here. So you can take some more time.
Okay, sir. Okay, sir. Thank you. Thank you to allow me. And it's a very nice group. Dr. Sweetie Kadan is presenting here. The same work I have because myself, Dr. Mahabir Barak, Department of Mathematics, student of Professor S.C. Malik from ICSDS University, Rohtak, and Sweetie is also my sister as a same supervisor. My research topic is effect of weather condition on profit analysis of a system reliability model with preventive maintenance and repair. Professor, I am audible?
Yes, yes, everything is fine. Go ahead.
Okay, okay, thank you. Thank you.
Yes, sir.
Please wind it off.
Thank you. Effect of weather condition means any kind of instrument or any kind of system when produced by any manufacturers, there is a long list with the system that how the system can be used and in which conditions the system can perform its best. These surrounding environment or these conditions are called weather conditions or environment conditions. The weather condition means is not means that there is an environmental condition outside the environment. Weather condition, according to my system produced by any manufacturer with a long list how the system can operate. These conditions are known as weather condition of a system. Weather is more effective to increase the performance of the system. Like there is a electrical fan work properly when there is a electricity between 220 to 240 volts. If there is a fluctuation between 220 to 240 or beyond the limits, may be possible the fan is not working properly. Same situation like here, suppose there is a motorbike, bike can be ride by a 2%. Company guaranteed wearing a helmet, speed is this one, condition is this one, then its average is 60 kilometer or 30 kilometer, that depend upon the brand of the bike. But in India or in our surrounding, the people are using the bike riding by 3%, sometimes more than 3%. They are working out of the conditions produced by the manufacturers. These are called abnormal weather conditions. Now, in 1985, Dillon, B.S. or Subramaniam, they discussed a stochastic models of a 2-unit outdoor electrical power system in changing weathers. Their changing weathers, that means the conditions used the power system. Changing weather means here is not meaning that environmental conditions. Same time in 1985, Goel LR and Sharma GC evaluates post analysis of 2-unit cold standby system under different weather conditions. In 1990, Goel Rakesh and PT Srivastava profit analysis of a 2-unit cold standby system with varying physical conditions of the repairmen. Singh SK in 1994 on the effect of weather condition in a 2-unit cold standby system. Wang Peng and Rao Bilton in 2002 reliability or post-worth assessment of a distribution system incorporating time varying weather condition and restoration resources. Billington Roy and Chengchen Wu in 2001 predictive reliability assessment of a distribution system including extreme adverse weathers. In continuing the work or in under the weather conditions in 2002, Bilton R and G.D. Singh's assessment of reliability of transition and distribution system considering the repair in adverse weather conditions sorry, it's my back. Wang Peng and Roy in again 2002, they assess reliability incorporating time varying weather conditions and restoration of the sources. Same time, 2005, the consideration of a multi-stage weather models in reliability evaluation of transitions and distribution system by Roy and Janak. Malik and Bark in 2007, myself, probability analysis of a single server system operating under the different weather conditions. Malik and Dheeraj in 2010, reliability and economic measures of a system with inspection for online repair and no repair activity in the abnormal weathers. In 2012, Malik and Savita analysis reliability and profit of a repairable system of non-identical unit with no operation and repair in abnormal weathers. Wards David in 2013, the effect of weather on grid system and the reliability of electricity supply. Louis and Yang in 2015, short-term operational reliability evaluation of a power system under extreme weather conditions. Burke and Nears in 2018 profit analysis of a 2-unit cold standby system operating under different weather conditions. Number of researchers are working on the same line, that 2-unit or 3-unit or n out of k units working in different weather conditions. But to increase the performance of the system, sometimes the cold standby unit may be possible out of order during unused of it for a longer period of time. Keeping the above study in mind, in view of the above referred study in mind, here a reliability model of a 2-unit cold standby system is developed, in which operative unit undergoes for preventive maintenance after a maximum operation time. The effect of weather condition on profit analysis of a 2-unit cold standby system under preventive maintenance and repair has been discussed in this model. The both units are identical in nature, which may fail directly from normal mode. It is our assumption. There is a single server who visits the system immediately whenever required and works only in normal weather conditions. It is the condition on the repairman that repairman can work only and only in normal weather conditions. Because in abnormal weather, when the server working in an abnormal weather, there is a chance to increase the either deficiency in the system or maybe any kind of loss. The operative unit undergoes for preventive maintenance after a maximum operation time. Repair of the unit is done by the server at its complete failure. The unit works as a new after maintenance and repair. It is also our assumption. It may be possible, sometime not such type of condition hold by any system, but in our system, we assume that the unit works as a new after maintenance and repair. The time to failure of the unit follows negative exponential distribution, while the distribution of preventive maintenance and repair times are taken as arbitrary with different probability density function, because we solved our model with the help of the semi-Markov process or Markov process, and distribution, negative exponential distribution follows memoryless properties. The expression of the several reliability measures are derived to study state using the regenerative point technique and semi-Markov process. It is our assumption that there is a stage S0 that is very initial stage. In this stage, one unit, namely as O, that is operative unit, and one unit you can see CS, that is cold standby units. There are two type of possibility. First possibility, the operative unit may goes for preventive maintenance after a maximum operation time. That rate is known as alpha naught. Second possibility is that the operative unit may fail. It is the rate, suppose lambda. It is our assumption. There are three type of assumption in our model. I see one by one. At the stage S0, there is one unit is operative, another unit is cold standby. There are two possibility, as you see last in last slide, this one. From S0 to S1, it is the alpha naught is the rate that operative unit goes for preventive maintenance after operating a maximum operation time. After there is a fixed time, like suppose I have a car, then company always offer me either you come back for service, either running a car 10,000 kilometer, or you can come to service by 3 months. It is the initial condition. Same here, operative unit after passing the maximum operation time alpha naught, it should goes for preventive maintenance that indicated as PM. And a cold standby unit replaced as a operative units. It may be possible, according to our second assumption, operative unit may fail with rate lambda. So operative units go for under repair. It is denoted as FUR, and cold standby unit take place as a operative unit as seen in stage S2. Similarly, at the stage S1, now there are two units. One is under preventive maintenance and one unit is in operative mode. There is a weather condition. Weather condition means when server is working, then in abnormal weather, server stop the work, any kind of mechanical work. So from the stage S0, there are four type of possibilities. First possibility is maybe environment becomes abnormal by the rate beta. So it goes to next stage. You can see there is a operative stage and PM. I indicated PM as a dark color. That means unit is under maintenance, but now maintenance is stopped due to server is not available due to abnormal weather. Another possibility from the stage S1 is that operative unit O goes for preventive maintenance after passing the maximum operation time. And possibility number third is that operative unit may fail with rate lambda. And the fourth possibility is that after getting the preventive maintenance with distribution FT approach to stage S0. So after getting the preventive maintenance, the unit becomes as a new and restore as a cold standby unit. There are four possibilities state S1. At the state S1, there are four type of possibilities. Similarly, there are four possibility at the stage S2 also. At the stage S2, one unit is operative O. Operative unit has two type of possibility. One possibility is that the operative unit goes for preventive maintenance after a maximum operation time with the rate alpha naught, and the operative unit may fail with the rate lambda. And another two possibilities are there with the second unit. The unit under repair may got repaired. So stage S2 to S0 under the rate GT. GT is the distribution of a repair. And another possibility is that under repair work, there is a abnormal weather with rate beta. So repair activity should be stopped in this one. Such type of assumptions, with carrying such type of assumptions, we complete the model.
Can you conclude in 2-3 minutes? We have taken too much time.
Yes. Yeah. This is the final model. I completed this model with the only three assumptions that maybe abnormal weather, maybe unit operative goes for repair, maybe the unit under preventive maintenance. I complete the such model. There is some, I think, visibility problems, but it can seem if you see carefully. This model is a system model of a two unit. One is operative, another is cold standby, with the assumption that this mathematical model can be solved with mathematical tools, with reasonable points techniques. These are the notation which I used in this model. OCS unit is operative, cold standby, alpha naught is rate by which the unit undergoes for preventive maintenance. Lambda is constant failure rate of the unit. Beta and beta 1. Beta 1 is the rate
Professor,
by which, yes, sir.
Yeah, you already taken 15 minutes. Can you conclude your study?
Yes, sir. Yes, sir. I just conclude within 1 or 2 minutes, sir.
Okay, thank you. Thank
you. These are notations which I used in my model, and transition probability and mean time to system failure. These are the simple calculations the transition probabilities can be verified that total sum of probabilities should be 1, that you can see in equation number 2. There are some probability or direct probability, there are some probability, there is a via probabilities. Mean time to failures, mean time, reliability to system equation number 5, phi I about this very simple, and equation number 6 can be calculated reliability of the system by taking Laplace-Stiltz transformation of system. Then we get equation number 6. Mathematically, I can calculate from, I can see equation number 7 is mean time to system failure, and same equation number 8 are the steady state of availability. These are the system equations of availability, and equation number 10, it is a standard formula to calculate the availability of the system, and n is here. You can see n is in terms of alpha, beta, gamma. That is the BG period of the system. These were W1, W2. It is the stage. At the stage, the server becomes continuously busy, either on a particular stage or via from a non-regenerative stage. And these are expected number of maintenance, which I found in my paper or this one. To analyze the behavior of reliability measure of mean time to system failure, availability, and profit function of the model, we assume that the weather fluctuation 20 times. First, I chose it, how many times the weather fluctuate in my system, that is 20. During the operation of parameter alpha naught, beta, beta 1, lambda, these are keeping as a fix. The numerical and graphical behavior by mean time to system failure, availability, profit function have been analyzed using MATLAB. Then what I found in this one, as the study reveals that a cold standby system with 2 identical units working under different weather conditions, the server works only in normal weather condition would be more reliable and profitable rather than increasing the maximum operation time. So idea of maximum operation time is not beneficial in the abnormal weather condition. That is my study only. I skipped the numerical and graphical part. These are the references.
Thank you. Thank
you. Suggestion, please.
Thank you. We don't have time actually.
Okay,
Okay,
sir.
thank you.
Thank you. Thank you. Sorry,
Yeah.
sorry.
So we Amit Singh Nair is here.
He is not presenting, sir.
Amit Singh is not here. Sanjeev is here, I think. Sanjeev Kumar, I see. Yeah, Anila is here. We have 3. Okay. Okay. Grishma. Okay. So please present Grishma. And you can take 12 minutes to 15 minutes maximum. Okay.
Okay, sir.
Yeah. Please stick on time.
Sure, sir. Sure.
Okay. Thank you.
Sir, I'm audible.
You are audible. You can put a Control L, so it will be in presenting mode. Yeah. Okay. Fine.
So, good evening, all. I'm Grishma Sundan, Research Scholar, University of Calcutta, and this is the joint work that done with my supervisor, Manohar sir. And the title of my topic is Reliability Estimation of Multi-Component Systems Model for NFE Distribution under Progressive Type 2 Synthesis Example. This is the outline of my work. Introduction. In reliability analysis, inference of the system reliability has received considerable attention in the last few decades. Generally, the system reliability R can be defined as probability of X greater than 1, where X and Y stands for the stress and strength variable of the system. And then The Bhattacharya and the Johnson in 1974 initially formulated the stress model for multi-component system, and it is given in equation 1. Here the x's are the random strength variable, which has the CDF fx, and capital Y is the common random stress having CDF fy. Okay, next is progressive type 2 sensoring. You know that most of the work are investigated under complete sample, but in many live testing experiments, the unit may lost or removed from the experiment before failure. So in such situation, the estimation procedure based on the censored sample are quite important. So among various sensoring schemes, progressive type of sensoring are most commonly encountered in practice. So under this sensoring scheme, we have n identical units are placed in the lab testing experiment. Among these, small n units are completely observed. And it has been done in such a manner that at the time of first failure, R1 units are removed. And then at the time of second, R2 units are removed. And this process continues until the nth failure occurs. And then all the remaining units are removed and the experiment will stop. Next is new flexible exponential distribution. It is formulated by Ijaz et al. In 2020, and the CDF, PDF, and hazard rate function of NFP distribution is given by equation 2, 3, and 4. Next is the system stress reliability. Here I derive the system stress reliability RSK. Here the Xi are the Xi are the random stress variable having the distribution NFP with parameter A1B, and common stress Y follows NFP distribution with A2B. Here B is the common parameter. And next is to estimate RSK. First we go through the MLE of RSK. Here for the case 1, that is when B is unknown, we can represent the sample as below. Here the exercise is a progressively type 2 sensor sample from NFP distribution with the respective sensory scheme. Similarly, YSBA progressive type 2 sensor sample from NFP A to B with the corresponding sensory scheme. To obtain the MLE of RSK, we first obtain the MLE of A1 cap and A2 cap, which is represented here. But the likelihood equation of B is something complex. So the estimation of B cannot be solved explicitly. Hence, we employ the numerical iterative method to find B cap. Once we obtain B cap, we can find A1 cap and A2 cap by just substituting B cap. And then using the invariance property of MLE, we can find the RSK, MLE of RSK. Similarly, in the case of non-B case, also we can derive the RSK, MLE of RSK as given below. Then next is the Bayesian estimation of RSK when B is unknown. Here we construct the Bayesian estimation based on squared error loss function and under the assumption that the parameters A1, A2, and B are random variable having the prior distribution as independent Rayleigh distribution with parameters sigma 1, sigma 2, and sigma 3 respectively. And based on the observed data, the joint posterior density function of A1, A2, and B are given below. We know that under squared error loss function, the Bayesian estimates of RSK is its posterior mean, and it is observed that this estimate is in the form of ratio of 2 integer, which cannot be solved analytically. Therefore, we use alternative method to obtain the Bayesian estimates. The two effective such procedure used here are Lindley approximation and MCMC method. This is the general definition of Lindley approximation. And in our case, we have three parameters, A1, A2, and B. And the function phi is equivalent to our RSK as in equation number 5. So substituting this value in the above definition, we get the Bayesian estimation of RSK. And here all the parameters are evaluated at A1 cap, A2 cap, and B cap. And next is the Monte Carlo Markovitch method. Here it is easily observed that A1 and A2 follows Nagagami distribution with their respective scale and shape parameter. And it can be also observed that the posterior distribution of B is not in a closed form, and it cannot be directly generated. So therefore, we use the Metropolis nesting algorithm to simulate the samples for B. So this is so we implement the following steps for estimating RSK. Finally, an HPD credible interval of RSK is constructed using the method suggested by Chen and Shaw in 1990. Next is the UMB of RSK. Here we find the UMB of RSK when B is known. The equation 9 shows the likelihood function when B is known. And here we define U and B as in equation 10. And it is obvious that B and U are the complete sufficient statistics for A2 and A1 respectively. Now to find the UMB of RSK, we consider the following theorem. So consider the complete sufficient statistics U and B as we mentioned above. Then the UMB of psi of A1, A2, which is a function that involved in the RSK. So we have to find the UMB of RSK. So just substituting the value of UMB of phi of A1, A2, we get the UMB of RSK. So we have put the UMB of phi of A1, A2 as in equation 11. So just substituting, we get the UMB of RSK. And next is the Bayesian estimation of RSK when B is known. So when B is known, we have two parameters A1 and A2, which follows independent Rayleigh distribution. And given below the joint positive density function of A1 and A2. Then by using the idea mentioned in definition and other 2016, we obtain the exact Bayesian estimation RSK as given below. Here we have the exact closed form for the Bayesian estimation. Even though for the comparison purpose, we also construct the Lindley approximation and MCMC. So Lindley approximation, as we seen earlier, here we have two parameters. Since B is known, we have two parameters A1 and A2. And just substituting, we got the Lindley approximation. So we got the RSK, estimate of RSK. Here also all the parameters are evaluated at A1 cap and A2. And next is MCMC method. We also observe that A1 and A2 follows Nagagami distribution. So we implement the following steps for estimating RSK. Here also we construct the HPD interval of RSK. And next is an extensive simulation study have been constructed to compare the performance of various estimation methods under different sensory schemes. So for this purpose, we compute the bias and mean square error for each estimate. Also, the behavior of HPD interval has been studied in terms of average interval length and associated coverage probabilities. All these have been done under different parameters, different parameter values, different hyperparameters, and different censoring schemes. For computational purpose, we use R statistical software. All these results are based on 1000 repetition.
Can you conclude in 2 minutes?
Oh, okay, sir. So this is the censoring scheme that we used in the simulation study. And this is the inference that we made from the simulation study. It shows that the Bayes estimate performs better than MLE for the estimation of RSK when B is unknown. And among the Bayes estimation, Lindley approximation are marginally better than MCMC estimates. And when comparing the Lindley's approximation between prior one and prior two, it is found that prior one provides better estimates and also prior two provides better estimate in the case of MCMC. And here we consider two set of parameter values. And it is observed that theta2 gives better performance in all proposed estimations method over theta2. And it is also observed that the HPD interval constructed using prior to provides smaller AIU value. And also the coverage probability of HPD interval lies close to the nominal level. And in the B known case, the MLE and the UMB are almost similar when compared in terms of absolute bias and NBC. Further, the bias estimate can be good against MLE and UMB except for the exact bias estimates. Here also we can see that the Lindley approximation provides better estimates than MCMC as in the unknowns. So as we compare the priors, here also prior one shows better performance than prior two in Lindley approximation. But in the case of MCMC, prior one and prior two are almost the same. And here also the theta2 performs better estimates than theta1 as in the case of unknown. amount B1. And it is also observed that the HPD interval constructed using prior to provides smaller AIL value for different combination of sensory scheme compared to the prior one. Here also we have the coverage probability of HPD interval are satisfactory and lies close to the nominal value. And further, the AIL value of HPD interval is smaller in the case of non-parameter compared to unknown parameter. Okay. These are my references. Thank you.
Thank you. Any question? Okay, let us move to the next presentation.
Thank you.
Sanjeev Kumar. Amit Singh is here? No.
That's Sanjeev Kumar here.
Huh?
Sanjeev Kumar here. Am I audible?
Yeah. Okay, please. Sir. Sanjeev Kumar, please.
Yes, sir.
Yeah, you please.
Good afternoon, everybody. First of all, I would like to thank the organizer for providing me this opportunity. Thank you, the chair and my co-participants. Am I audible, sir?
Yes. Fine.
So the title of my presentation is A New Repair Replacement Strategy Considering Two-Dimensional Warranty Data. So first of all, I would like to introduce the term warranty, which is an important marketing tool. So what is warranty? Warranty is basically a contractual agreement between a manufacturer and a customer through a dealer by which the manufacturer agrees to repair or replace the product when the purchased product fails to function as intended
Some extra voice, sir, behind it, please.
within a stipulated limit. So the main purpose of warranty. Yes.
Sanjeev sir.
Yes.
There is an extra voice, sir, behind it, I think.
Some ground. Yeah.
Behind you, lot of noise is coming.
Hey, Nitaida. Oh, Nitaida, একটু চুপ করে এটা পড়া পড়াচ্ছি। Is it okay now? Is it okay now?
Yeah, please continue.
Okay. So warranty is a contractual agreement between a manufacturer and a customer to a dealer by which the manufacturer agrees to repair or replace the product when the purchased product fails to function as intended within a stipulated limit. So the main purpose of warranty is to make liability among the two parties, that is customer and manufacturer, in case of an item fail. So both the parties, that is customers and the manufacturers, at a respective stage. From the customer's point of view, warranty gives a financial guarantee towards quality and reliability of the product. On the other hand, from a manufacturer's point of view, warranty impress upon the prospective customer about the superior product quality and reliability, and also it gives assurance to carry out an effective post-sale service toward better customer satisfaction. Warranty or analysis of warranty data generally deals with this following topic: early detection of reliability, design modifications, reliability estimate, claim or cost prediction, and claim or cost estimation. So basically, if we divide warranty, then we get two types of warranty. One is one-dimensional and another is two-dimensional warranty. One-dimensional warranty is generally guided by only the age of the equipment. For example, say the warranty of an electronic item is 3 years. So here, warranty is extended up to a certain age. On the other hand, a two-dimensional warranty is guided by both the age as well as usage of the equipment. So here, warranty is extended up to say certain age and certain usage, whichever is earlier. So this type of example mainly exhibited in the field of automobile. For example, the warranty of an automobile 3 years and 36,000 miles and etc. So this is a graphical representation of two-dimensional warranty. If we put the warranty limits in the center, then we can get 4 quadrants. In the first quadrant, which is known as reliability region, here time process is time limit and usage also process is usage limit. This is the warranty region. Here time does not process is time limit and usage also does not process is usage limit. And if an item fail in this third quadrant, then the buyer or the customer claim warranty, because in this time period he or the manufacturer may provide service free of cost or take a small amount of cost. So if an item fail in the region, then the manufacturer can get an idea about the failure time and usage. So this is the overuse region. Here warranty is expired because usage process is usage limit. And this is the fourth quadrant, which is underuse region. Here warranty is expired because age process is limit. So among these 4 quadrants, only if an item fails in the warranty region, then the manufacturer can get an idea about the performance of the vehicles or automobiles. So this is why the data within this warranty region is incomplete, and it is required to model and analyze the warranty data for different purpose from this incomplete warranty data. And similarly, we can get the age reliability and usage reliability based on these 4 regions. So how can we get the age and usage? So in any manufacturing company, generally we can get this column. So first column indicate the vehicle identification number, then we have production date, then we have date of sale, then we have usage, and then we have claim. So if we subtract the date of sale from the age, and from the 4th column we can get the usage of the column, which can be obtained from the odometer. So whenever we model warranty data, so one can apply one-dimensional approach. Here the age and usage can be separately treated, separately modeled. And another approach is two-dimensional approach, which is logical in this case. And here we have 3 approaches. Firstly, we have, which is bivariate approach. Here we can consider the joint distribution of age and usage. The second approach, which is not in composite scale approach, here we can take a linear combination of age, usage, and then model the composite scale. And the last one is a conditional approach, where the joint distribution of age and usage can be modeled using the age and usage rate. So among these approaches in this paper, I only concentrate on bivariate approach. However, other analysis that we want to discuss here may be done applying conditional approach and composite scale approach as well. So objective of this work is to construct a bivariate warranty model of age and usage on the basis of incomplete warranty data, to compute the number of mixture of distribution, if any, and to segregate the warranty region further and propose different types of repair actions. So as it is an incomplete warranty data, so it is required to EM algorithm to estimate the model parameters. So this is a likelihood function. If an item belongs to the fail in the warranty region, then its contribution will be FTIM, F of EIMI, and if it does not belongs to warranty claim, then it is unobserved. So this is why we have to apply the E step, and E step means we have to take the expectation of this likelihood function, and this is the M step where we have to maximize this Q function. And apart from the AIC or some standard criteria, we can validate the model with this type of statistics, which is known as efficiency. This is basically a comparison between the observed total number of items and the expected total number of items. And if EFF closer to 100%, then the model is better. In fact, better. So we have considered the bivariate log normal distribution. Let there are 3 mixer and certain parameters with certain mixers. So we make the following transformation, that U equals to log T and V equals to log M. So it is obvious that U and V will follow a bivariate normal distribution with certain parameters. So this is, we actually deal with a mixer of bivariate normal distribution in the sensoring setup. So we divide observed data and unobserved data, and then we also define the mean vector and the covariance matrix in this following way. So then we step the each step and end step. In fact, Lee and Scott have also applied this type of problem, but they have considered only the warranty region and the reliability region. They have not considered the underused region and overused region. So in our purpose or in our study, we have considered both the underused region and the overused region also. So following the, we have write down the each step for this bivariate log normal distribution, and hence we can derive the estimates of parameter in the m step to maximize the q theta function. So for this m step, we need to MC algorithm. So for this purpose, we have draw the unknown observation from the truncated bivariate normal distribution. So in this here, we require to draw the sample from underuse, overuse, and reliability region also. And for this purpose, we apply each sampling separately to draw sensor sample for this region, keeping in mind the expected proportion of items in the region for the given criteria. So on the basis of this estimate, one can evaluate the proportion of items in overuse, underuse, and reliability region. And using this proportion, say N1, N2, and N3 number of observations, these numbers are drawn from overuse, underuse, and reliability region, so that N1 plus N2 plus N3 equals to N minus capital N minus small n, where small n is the total number of items within warranty, and N equals to the population size. In each iterative step, the same operation to generate sample from the different regions are performed. So here the values of N1, N2, and N3 may also be changed in every step. So repeating this procedure several times of time and taking average of each parameter separately, one can get the value of this parameter. And the number of Gaussian mixture with say A or N star parameter may be determined from the AIC criteria. So
please conclude in 2-3 minutes.
Okay, sir. So this is the segregation of the warranty region. So we have further segregate the warranty region with respect to zeta and eta, and then we have proposed different type of repair replacement strategy. So if it belongs to this region, that is early failure within warranty region, then a perfect repair is expected, because it is expected that this item fails because of manufacturing defect. And on the other hand, overused region and underused region, the minimal repair is suggested. Similarly, we have also taken a point here, xi and chi, and up to this point, in this region, it is expected that items fail because of manufacturing defect as well as what usage related defect. And other, so here a imperfect repair is proposed, and other regions we propose the minimal repair. So, so we have also estimated these reference points. So for this, for the first time or the first zeta and eta, we have find the empirical hazard at different age points. Divide the time scale into 2 parts considering various age usage points, and fit the linear regression for 2 parts with various age division points. Similarly, linear regression for 2 parts with various usage division points. And then we have computed the empirical ratio for the and partition for every partition point, and computed the minus twice log ELR. And here we have maximized this function, and then if we get for this value for nanity, then we take the minimum of the for which is maximum takes place. Similarly, we done this for the usage parameter. Similarly, the other points, that is xi and chi, are also determined in such a way that probabilities in this expression is equals to alpha, and among the different points of xi and chi satisfying the condition, it is suggested to choose the pair for which that xi minus chi become minimum. So this is the formula. So, and then we have estimated the expected cost for perfect repair. We have taken the convolution, and for minimal repair we have taken non-homogeneous Poisson process, and for imperfect repair we have taken PQ imperfect repair policy has been implied, and this is the expected cost. So we have taken a real life data, and based on this we have for different mixer we have estimated the AIC criterion after estimating the parameter. And here we have seen that when k equals to 3, it takes the minimum value, so number of mixer of 8. Then we have estimated the parameter using our approach and also leave and spot approach, and you can see the efficiency in case of our approach better performs than leave and spot approach. And then we have also estimated the change point towards the S direction from synthetic data from the real life data. And here we have seen when the month, and this is the maximized when the t equals to 4. And with respect to Km, this is maximized when K equals to 6. So in this way, we have estimated the references point, and also the xi and chi are also determined respectively in this way. And on this basis of this, we have also a real life data. So based on some of this, we have estimated the expected cost, and this is 183 units of money. So this is the real life example. So these are the few selected references. And thank you.
Thank you. Thank you. So, thank you for the presentation. We have Anila.
Yes, sir.
Yeah,
Is
yeah.
it audible?
Yeah, you can.
Oh, okay.
12 to 15 minutes.
Okay, sir.
Okay, thank you.
Is it visible, sir?
It's coming.
Yeah.
Yeah, you can press F7. Okay.
Yeah, but it's not coming, sir.
F7.
Yeah.
Something
It's
is happening.
slideshow.
Yeah, slideshow.
From beginning. Yeah, is it visible, sir?
Yeah. Okay.
Okay, sir. Myself, Anila P. I am a guest lecturer in Department of Statistics, Cochin University of Science and Technology, and it's a combined work with V. Kavirasu, Assistant Professor, Department of Statistics, Bharatiyar University. And the topic of our paper is that development of quick switching single sampling system 2 for percentage life under log logistic distribution. Now coming to the keywords, these are the keywords I included in this PPT: statistical quality control, acceptance sampling plan, single sampling plan, reliability sampling plan, log logical distribution, and quick switching system. Okay, so first of all, I am moving to statistical quality control. That we all know that quality control is a technique which the statistical tools that is used by the quality professional to check the quality. And there are two categories: process control and product control. In my paper, I included the product control part. Then acceptance sampling plan means it's a decision-making criteria whether to accept or reject it. Or OC curve is a performance measure. Then I am just differentiating the sampling plan, sampling scheme, and sampling system because I am using sampling system in my paper. Sampling plan is that it is a specification of the rules to be followed in sentencing any particular batch of article. This definition is given by Hill in 1962. And sampling scheme is that it is an overall strategy specifying the way in which sampling plan are to be used. Examples of sampling scheme are military standard 105D, Dodge and Roaming, LTPD, and AOQL tables, etc. And sampling system means that it is an assigned grouping of 2 or 3 sampling plans, that the rules for using these plans for sentencing loads or batches of an article to achieve a blending of the advantageous features of each of the sampling plan. So example of sampling system is quick switching system is an example of sampling system. Then in my paper, I designed a quick switching system in which the reference plan is single sampling plan with reliability, or the reliability single sampling plan. So just I included the single sampling plan here. Okay. Then moving to reliability sampling plan, or as we know that many of the product has many type of quality. Whenever we are dealing with a lifetime of a particular product, we can use the reliability analysis to our sampling plan. So reliability sampling plan means sampling plans are used to determine the acceptability of products with respect to lifetime are known as reliability sampling plan. For that purpose, I use the log logistic distribution. That means here the lifetime is considered as a random variable, and that random variable have a distribution. So I use the log logistic distribution, but because that in QSS it's rare to use that much of distribution. Only some of the others used distribution in QSS, and log logistic distribution is not used. From my review, I understood that. So I use log logistic distribution, and the probability density function of the log logistic distribution is given by equation number 1, and the cumulative distribution function is given by equation number 2. Here the gamma is the shape parameter and sigma is the scale parameter. And Kantham et al. Introduced the log logistic distribution in acceptance sampling plan for truncated life test. Then moving to the a survival function and hazard function. This is a survival function and hazard function of log logistic distribution. Now the percentile estimator, I found the percentile estimator. That means, first of all, it is important to note that CDF depends only on T by sigma, since the shape parameter is not. And the qth percentile of log logistic distribution is given as equation number 3. And the probability that the product fails before the experiment time T0 under the log logistic distribution is given as equation number 4. And according to Aslam and June, one can study the experiment time as a multiple of the specified qth percentile life theta naught, that is T0 equal to A theta naught for a constant experiment termination ratio A. Therefore, the equation 4 can be written as equation 5. And moving to the Quick switching system, I am briefly explaining what is Quick switching system. Actually, the Quick switching system is proposed by Dodge, and after that Rombosky studied with QSS with SSP, that means single sampling plan as reference plans, and there is 5 parameters in QSS. The first one is N sample size, then CN and CT. CN means the normal acceptance number, CT is the Titan acceptance number, and next is PN and PT, that means probability of acceptance of normal and Titan inspection. And there is 2 type of QSS. The first one is QSS N CN CT. In that, CT always less than or equal to CN. And the second one is QSS N KN C0. Here the acceptance number will be same and the sample size will vary. So I used QSS N CN CT in my paper. Okay, and the Quick switching system has 3, QSS1, QSS2, and QSS3. I use QSS2 for my paper. Okay, this one. Then these are my reviews for single sampling plan, reliability sampling plan, Quick switching system, and Quick switching system with reliability. And the last one is log distribution. These are my reviews. Then moving to my contribution part, that means acceptance sampling plan for truncated life test under log logistic distribution, assuring percentile life through QSS2. So first of all, these are the conditions for application of QSS2. The first one is that the production is steady, so that the result on current and preceding lots are largely indicative of a continuous process. And the lots are submitted significantly in the order of production, and 2 consecutive lots are to be accepted in Titan level. Then just moving to the steps of QSS2, first of all, we will start with normal inspection and we will inspect it. If D is less than or equal to CN, we will accept it and we will continue in the normal inspection itself. If the lot is rejected, we will directly go to T1, that means Titan inspection level 1. And in that case, if the lot is accepted, we will again go to Titan inspection level itself. That means 2 consecutive lots are to be accepted. Then after that, the lot is accepted, we will directly go to normal inspection. This is the steps of QSS2, Quick switching system 2. And Rombosky has derived the OC function of QSS2 as equation 6. These are the steps. First of all, we will select a random sample of size n and count the number of defective in the sample before the specified time T0, and we will denote it as dn. If dn is less than or equal to cn, we will accept the lot, and if dn greater than cn, we will reject the lot. And after the rejection, we will directly go to, that means switch to tightening inspection. And under tightening inspection, same procedure, we will select a random sample of size n and we will count the number of defective and we will denote it as dt. And we will compare the dt with our Titan acceptance number. If dt is less than or equal to ct, we will accept. If dt greater than ct, we will reject, like that. Then how I constructed the tables, that means I designed an QSS system. So I obtained the parameters. For that purpose, these are the steps to determine the parameters of QSS. First of all, we will fix CT equal to 0 and CN equal to 1. Then determine the values of NS as the smallest value of N satisfying PA of P2 less than or equal to beta. and then determine the value of NL as the largest value of N satisfying PA of P1 less than or equal to 1 minus alpha. After that, if N is less than or equal to NL, then the QSS satisfy the condition has the parameter N equal to NS, CT equal to 0 and CN equal to 1. If NS is greater than NL, we will increase the value of CN by 1 and repeat the steps again. And 6 tables are constructed using the above procedure. Okay, 1 second, sir. Okay. Is it visible, sir? Is it visible?
Yes, ma'am.
Okay. Okay, fine. Okay. So in this study, the optimal parameters of the proposed QSS2 for assuring 20th percentile and 15th percentile life are carried out here. And the percentile ratio is described by, this is a percentile ratio described by 2, 2.5, 3, 3.5, and 4 at the producer risk, and the ratio is taken as 1 at the consumer risk. And for determining the optimal parameters, various values of shape parameters as considered. Here the gamma equal to 1, and the next table is gamma equal to 2, and the next table is gamma equal to 3 for 20th percentile. And the producer risk is fixed, that is 0.05. I fixed it as 0.05, and the consumer risk are taken as beta equal to 0.05, 0.10, 0.25, 0.01. And the experiment termination ratios I have fixed as A equal to 0.5 and A equal to 1. So I constructed 6 tables of 20th percentile and 50th percentile with gamma values 1, 2, and 3. These are the tables. From itself, it is clear that when the theta q by theta naught, that means percentile ratio increases, the sample size is decreasing. Percentile ratio is increases, the sample size is decreasing, and this is the first table of optimal parameters of QSS2 for 20th percentile under log logic distribution with gamma equal to 1. Here it's 20th percentile and gamma equal to 2. And the next table is for gamma equal to 3. And the fourth table is that QSS optimal parameters for the QSS2 for 50th percentile under log logic distribution with gamma equal to 1. These are the tables. This for
could
gamma.
you please conclude within 2-3 minutes?
Okay, sir. Yeah. And this is OC curve of QSS2. I constructed an OC curve regarding the table 1. That means QSS for 20th percentile under log logic distribution with gamma equal to 1. And the experiment termination ratio A equal to 0.5 and the N equal to 22, Cn equal to 5, Ct equal to 0. This is the OC curve of QSS2. Then coming to the example, I have taken the data discussed by Scheme and Nelson and show the number of thousands miles at which different locomotives control. For that purpose, I used QSS2 for assuring 20th percentile life, and I fixed gamma equal to 1. Here alpha equal to 5% and beta equal to 25%, and the percentile ratio is 4. So I specified the percentile of the product theta naught equal to 47 and the experiment time T naught equal to 47. So the termination ratio A equal to 1. So from the table 1, we can get that N equal to 8, Cn equal to 2, Ct equal to 0. By regarding this, we are going to construct the table. Okay. First of all, we'll start with normal inspection and select a random sample of 8 units from the lot and put them on the life test for specified time 47. Suppose that 8 units are having failure time as follows. This is the failure time. So here 3 values are less than 47. So here Dn equal to 3. So the lot is rejected. We will directly go to Titan inspection. Under Titan inspection itself, we will take a sample size of 8 and we will inspect it. Here no failure, no defect is there. That means dt equal to Ct. So we will accept the lot and continue in the Titan inspection itself, because 2 consecutive lots are to be accepted. So we will continue in itself and we will go to another sample, taking another sample of 8. then we will count the number of defective here to dt equal to ct. So it equal to 0. So we will directly go to normal inspection. That is, we will accept the lot and 2 consecutive acceptance occur under Titan inspection. So it can be switched to normal inspection for the next lot. So moving to the conclusion part, a new reliability sampling plan is constructed under log logic distribution, assuring percentage life through QSS2 and determine the minimum number of sample size n for several values of consumer risk percentage ratio. Then from the tables, it is clear that the sample size of the quick switching system is decreases when the percentage ratio increases. And these are the future studies. That means for future study, this was also extended to design a reliability sampling plan for various percentage levels for the other continuous probability distribution. The efficiency of the proposed sampling plan using a coarse model can be considered as a future study. And the developed plan helps to improve the consumer-producer relationship by maintaining the quality consciences at all levels. And these are my references. And thank you.
Thank you.
Okay.
Anybody have any question? I think all the students, means all the speakers presented. So we will conclude this section, today's session. Okay. Thanks.
Thank you so much.
Thank you, sir, for chairing the session. Thank you.
Thank you.